to time domain to frequency domain in order to get some information and confirm, some data. Of course, one of the most, used approach is utilizing Fourier transform, which of course has the disadvantage of modeling any signal by a sum, or a discrete sum of sine and cosine periodic functions. So, roughly, if one wanted to study a single peak, it would be, somehow not that easy. On the other side, there is this other approach, which is continuous wavelet transform, CWT, sorry, C is in Italian, which of course allows us to have the same response, but it fits, the data according to a sum of discrete interaction of a wavelet. I don't want to stress you with this wavelet, but roughly the idea is the following. So, first of all, a given wavelet is chosen. A wavelet is, a given signal whose integral is 0 along its definition. So if I do the integral of the product of the signal times the wavelet, and I just produce different stretching factor of the wavelet, it is usually referred as voices per octave function. And if I shift the wavelet along the data set, I can record three kinds of information. The K, which is a function of the period, the time, which is the shift, which is a function of the time, and the product, which is a function of the intensity of the signal. This produces the upper left plot, which is also usually called the scalegram. Okay, so on the right side panel, you can see I plotted, a sort of limits in the period that can be estimated according to the database length. Of course, the lower one is only a function of the fact that the database is annual. It is always 2.7, while the more is the length of the data set, the more is the period, the farther I can go within the period estimation. That's roughly the idea, but we said, okay, yeah, this is a good tool. This was, somehow suggested us by Usoshkin. So we said, okay, why don't we test it? And this is a test that I started doing after the goal with Gianluca. So roughly, the idea could be I produced a signal made by the sum of three different periodic functions. So it should be, we will see, 20, 10, and 4 years. I just give this signal at the code doing CWT analysis, and you can see that this is similar to the scalegram applied to our figure, and you can see that there are, appearing three main periods, which of course corresponds to the signal we built. And of course, it's very nice, this tool, because it can either be inverted. Because, yeah, one can, for example, decide to sum all the period and get the red. Is it red? Yes. Get the red lower panel right function, which, should fit accordingly the data. Of course, there are, border effects on the left and right side of the plot. Or one can use it, for example, to select a given frequency. But that's, something not very, very new. You see here, I just decide to integrate the gray interval and get the periodic signal. And in this plot, it's compared by two gray lines. One is the original signal, and one is the reconstructed by means of CWT. So very nice tool. But at this point, some of my students, of physics laboratory, they know this. What about uncertainty? So Usually, a scaleogram is always produced by your data, but usually the data we use are affected by uncertainty, and so we need to take uncertainty into account in order to evaluate the significance of the produced data. So we used, in this case, the tool for the lazy person, Monte Carlo simulation, 1,000 simulation of the same data set I showed you before, in order to estimate the uncertainty affecting each produced scaleogram, data in the scaleogram, and combining the two, we can produce an index, which, of course, quantify the statistic significance of, the period present in our data. And here you can see in red we integrated because, you can see I just produced the noise, which was comparable in amplitude to the smallest period we were using. And so, of course, our software, our code, how does it work? I don't know. Yeah, there, you can see the lower, upper right panel, you can see there is 2 of significance. So it is still good, but it can be used to filter data compatible to the noise. And so, of course, in this case, you can have a sort of measurement of the periods that are present really in your sample. Oh, we did some other testing. I will be fast. I don't have the clock, but yeah, you probably have it. 10 minutes. Okay. So, sorry. We just decided to perturbate our data set by applying 5% random variability to the period, again with Monte Carlo, and that's an example. You can see, sorry. Oh, what I did. Yeah, okay, this was the first one, and after the perturbation, things sounds to change slightly, but again, the index, statistical index, tells you where to integrate the data. And again, by comparing the red plot with the gray plot, you can see that there is a good agreement apart from the borders of the interval. Since we were interested in getting peak, so we decided to add to our signal also a peak, which is, something very simple, just a spike decaying exponentially with the decay rate reported there. Now this is for 1. That's the scaleogram produced for the peak. That's the total scaleogram, and so again, this is the window of integration, and you can have the signal here, and you can reconstruct the peak. Hereby in black, the lower right, we'll see the signal, the differences with error propagation, and overlapped the original signal. And you can see that, it gets the signal. Of course, it gets signal in similar periods, for example, for faster decay rates. If we, for example, leave the decay rate to 1 and increase the uncertainty affecting the point, this, of course, will affect our sensitivity in detecting the signal. So, message learned, our code, it's a MATLAB code, get signal, but one should pay attention to the sensitivity, or to the uncertainties affecting the data, because of course they do have an effect onto the sensitivity of the model. And of course, another thing to pay attention, I did not show here, is that if the peak is too wide, we will see it starts falling onto the other period appearing. It is probably the case we will discuss later. Later on, there was this paper, yes, there are also you, yes. Yeah, okay. So thank you for this data set. It was a good gym for us. So in gray, light gray, the data set. Sorry for this representation. It was the only one visible. I don't like it. There are no errors. And these are the wavelet we use it to fit the entire data set. There is 200-year period, 105 period, and 59 periods. Likely, if one focuses attention onto the lower left of the figure, one can notice big bumps So it's Miyake event 993 and 1054, 55, whatever it is, okay? And in fact, that's the situation for the Miyake event. Using your data, you can see we added the fourth period. So the idea is that we cannot, I showed you before, add small periods if we don't split the data set. And this is the plot overlapped of the period. You can see that there is a strong periodicity soon. If you look at the lower right panel, there is a strong periodicity in the upper part of the plot. And what is happening into the lower part, surrounded by 2 and 3, iso-ipsa, it should be the Miyake event. But if we add this periodicity, it produces the green one. So it can be, there is a sort of interaction between the data. And that's only the Miyake event, lower part of the lower right panel, deconvolved by the data set. Similar to the paper, we just also compare data set produced on the Schwabe signal, which is, somehow around 10 years. It can be either estimated precisely the period of the Schwabe signal, and we compared with sunspot, annual sunspot, the one I showed you before. Wavelet has also the opportunity to do comparison between data. And this is the result. It is called wavelet coherence. So you will see colored, the point of coherence, and the arrows indicates the phase shift between the periods. So at the beginning, there is a complete accordance with the phase, the first block in the lower right plot. After, there is a sort of shift, but you can see also from the data. And after, it goes back to the same agreement. So again, a good result also here. Let's come to the 1054. Yeah, I will just keep it, I'm going fast. For this signal, which appears, we will have the time to discuss this smaller, with respect to the period, there is no overlapping with the Schwabe effect, and you can see here the signal deconvolved and the data, and also in the paper, this event was classified, as extra production of C14. Resuming, this was the beginning on the left. On the right, this was including BREM dataset and the wavelet. And you can see that net difference now appear higher than 2 sigma. So either higher, for example, for the pine and the sequoia, it's, somehow close to 3 sigma of difference. Yeah. Let's compare this data. We see that roughly Miyake happens onto a slower time scale, while our signal, our 1054 happens onto a smaller scale. Oh, this is very, very preliminary. So I told Filippo that I would not show this data, but okay, no matter, he's not here. So there is a reason. This is a collaboration with Jonathan Palmer in South Wales University, Australia. Black points are quite affected by very, very small errors. White ones, no, it's ours. That's why Filippo would like to avoid showing this data. Yeah, this is not a very lucky measurement. At a certain point, we got several power failures, so the data set is not good. But what can we do with this? And how can we use, for example, wavelet analysis? You see that for Southern Hemisphere, there is a strong problem. Yeah, 5 minutes. We don't have any annually resolved data set. You should do that. Also there. Okay, yeah, Jonathan did some, okay. So how to fix this problem? Due to the fact that the wavelet analysis does not take into account for bias in the values, let's see this. just to waste my time, compare the data set with the one with big errors, the one with the low errors, with the BREM data set, and you can see there is a strong coherence between the period, 10 years, it's comprised in this period, between our data Palmer data and Brem data set. Of course, strange thing, one can see that the arrow points to the left. There is a 2 pi phase of difference, which in that period correspond to circa 2 years of difference, but probably you can notice either into the lower left panel, the peak red and the peak in white, black is somehow shifted 2 years before. The data set, ours, Chirche and Palmer are coherent, but of course this does not take into account of error, wavelet coherence. It can be done. I did not have time to do that, but it can be done. So, what else? What can model? How can model help us? I guess also in this there is, this is model. We just try to model. So, is it still valid, the idea of the supernova or not? You claimed it is solar proton events. It can be, but I mean, the main point against supernova is that it should be too much strong, and I mean, charged particle cannot interact and produce radiocarbon. Only gamma particles can interact with the atmosphere. They are much more, they go deeper into the atmosphere. But of course, gamma particle is only 10% of the produced energy of a supernova explosion. But with this plot, we wanted just to, highlight a point that gamma, of course, should be interacting, closest to the lower part of the atmosphere. And in this plot, by 10, 40, and 75% for different hemispheres, I don't want to waste too much time on this because I'm finishing. You can see that if you increase the fraction of radiocarbon produced directly into the troposphere, as it should be for gamma, you have a prompt peak with a prompt increase and a prompt decay. So it goes toward the verse of the 1054 AD with respect to the Miyagi event. And this is also a simulation with it. For our data, not important, not so much important. The message is exactly the same. Thank you. Just a second. So if you stay here on Friday, if you are here on Friday night, there will be the European Researcher Night. So they will be here in Lecce, Erna Puriamed, but if you'd like to come to Naples, there is also streets. Also, and I will go back for that, sorry. Please.
Thank you very much for this nice introduction into the tools that we use for analyzing these annual tree rings. Are there any questions to the talk?
At the beginning, you mentioned the Chinese observation of supernova, yeah? And somehow I had the feeling you related this peak possibly to a supernova event. Now, in case it was a supernova, of course it was observed visually, and only gamma rays would travel at the same speed as, so. Yeah. It cannot be induced, it cannot induce carbon-14 by particles, which would be a big shift in time between the optical observation. That's my feeling.
Yeah, in fact, supernova was observed, it's just, I'm not claiming anything, I'm just saying, it could be, yeah. It could be. You see supernova, it was in July, or August 54, we see the peak in 55. Yeah, of course, one can see, this works, sorry. One can see data fits. Of course, the amplitude, yeah. There is something to say. the main argument against the supernova is that, I mean, the amount of gamma allowing us to see this signal should be tremendous with respect to the one produced.
So there must be
But of course, this estimation is based always on to the 70-30 percentage. While if you go below, so if you go to 10%, the inverse, and you just hypothesize that production is mostly located downward into the troposphere, yeah, there is only a factor 2 or 3 of magnitude that we miss somewhere. We are discussing with with astrophysicists in order to try to see if it is, I mean, feasible or not. We have not claimed it's supernova, but you know, it is Filippo ideas,
Intriguing,
and we like it to bring it on. It's not, I mean, a claim. It's just, I mean, observation, just
Okay.
ideas.
Thank you.
Sorry.
Are they?
Periodicity period of 200 years when you reconstruct over, yeah?
Yeah.
Is this driven by the Miyake events? Because it's more or less the difference between the
Sorry.
first two Miyake events.
I was just trying to recall
You have
the.
different, let's say, components.
Yeah. Let me. No, this is not. Do you this one
Yeah.
or the previous one?
The first wavelet period, it's 200 years.
Yeah.
Right? And is this driven by the time difference between the two Miyake events, 773 and 9?
Yeah, I don't know. At present, so I did this calculation when you invited me. So their data set was very nice because there is Miyake.
In principle, one could run
Yeah.
this system over the entire.
Yes, but then I mean, of course, the limiting factor is the resolution of the data set. We need the annual one, of course, if you want to, I mean, go in the details.
And also other effects which are not periodic.
Yes? Yeah, there are.
Maybe a last question.
So these periods are interesting, but there's a lot of previous work on solar cycle periods, and we know that the Schwabe cycle is 10, 12 years. But some of these longer periods, have you compared them to other previous estimates of longer solar cycle periods? Like, I think there's one about 180 years, just to compare previous work.
Sorry, I did not get the question.
The question is, there's a lot of previous studies of C14 cycles, which are then interpreted as solar cycles, such as the Schwabe cycle and the Gleisberg cycle. There's a whole bunch of them. There's one about 180 years, and yours seem to be different in those numbers. I was wondering if you had compared your data to those other estimates of solar
Oh, yes,
periods.
yes. I did it, yeah. Not here, but yes. Of course, we are aware of the other, I mean, the other estimates. We can compare. Of course, it's just, I mean, last second work. Sorry. Yeah, I finished yesterday night to do my last slide, so of course it can be done.
Okay, thank you for the discussion. As you may notice, the chairperson is changed, and as now I would like to introduce the next speaker, who is Lukas Wacker from ETH Zurich, and he's going to show us the annual record for 5,600 years and how can you see the solar and magnetic fields influence on this record. Okay, Lukas, floor is yours. I can see your presentation here, but okay.
Yeah, thank you very much for the introduction. So I pretend to present a lot today. It's not quite that much that I will present it. I think also the 12 minutes are maybe a bit too short, but I will pick out some parts of this nearly 5,600 year record. And what I would like to do is to show you a little bit what we can read about the sun in this record. Here you see the 11-year cycles as observed over the last 300 years. And what you can notice is when you go back in time, I don't know, there in the mountain minima, there are hardly any observations of 11-year cycles. That might have actually several reasons. Maybe that the observations were not so good. Certainly they were not so good, but also there probably were no 11-year cycles. But you see that we have this nice record, but suddenly it stops and we don't know what happened before. What did the sun do before? And for this, we have to look into tree rings. That we look into tree rings is actually not new. So this is Douglas, who started to study more than 100 years ago 11-year cycles in tree rings. And he thought that he would see in the ring width changes depending on the solar activity. And he was, until he died, he was not sure whether he saw it. And still today there are some people who sometimes think one could see the 11-year cycles in tree rings. But I personally actually think you don't see them, and it's always a bit, to see some wiggles is always easy, but whether they're from the sun or from something else, that's the big question, and that needs to be shown always. But we can use now C14 to increase the chances that we really see the 11-year cycles. So when we have a strong sun, then we have more sunspots. So there is a direct correlation. The correlation with C14 production in the atmosphere is actually opposite. So when the sun is weak, we have an increase in C14 concentration in the atmosphere because the production is high. So we actually published, this was presented in the presentation before already, this 1,000-year record where we analyzed the tree rings. That was some years ago. What you see in the upper left figure are the delta 14C concentrations. So we see variations in C14. And when the concentration are rising, then it means we have a higher production, and that means we probably have a weak sun during these times. If you want to get now the production, we need a carbon cycle. Here you see a model also of the carbon cycle, basically a little bit how you calculate. The C14 is produced in the upper stratosphere and is then transported in the carbon cycle. And the atmosphere is only actually a small pool of the carbon cycle. And so it needs to be modeled, otherwise you don't get the right result. We did that, and now we have the C14 production, and you see it's an up and down, and you see really periods where there seems to be a lower C14 production. Now this is not exactly what the sun did. It would actually be the inverse rather, but we still have to apply correction. We have to apply a correction for the strength of the Earth's magnetic field. What we then also do to eventually get then what we call the solar modulation as a measure for solar activity. And when we look in the figure on the right, on the bottom, then you see the observed 11-year cycles in black, and you see on top in orange you see the solar modulation, and the solar modulation does something really similar to the 11-year cycles, what means we probably can detect the 11-year cycles, and it's all synchronous and seems to be very nice. But you also see that when we go into the mountain minima where there are no observations, then actually also probably the 11-year cycles start to disappear basically, even in our C14 record. Maybe it's still something there, but not very strong. And when we go then in solar maxima, we seem to see more cycles again. So this seems to work, and we could actually publish this. To really prove the main part of this paper is actually that we try to statistically prove that these cycles are there. For this we did some Monte Carlo simulations. What you see here is we just measured in principle the heights of each cycle. So when we have a wiggle in our spectra, then we measure the heights, and we get the distribution that's in orange, a distribution what we have measured. if we create a pure noise record and we analyze it in a similar way, then we get the blue curve in the back. And on the uppermost figure shows we put in no signal at all. It's a pure noise record, and we see that we have not such a good agreement. When we overlay our noise record with a sinus with a length of 11 years, then at an amplitude of about 0.8 per mil, we get a good agreement. When we go then further to, let's say, 1.5 per mil, then we see we have no good agreement anymore, and that leads us to the conclusion that we have actually an amplitude in our record on average of about 0.8 per mil. So now what we have analyzed in the past was in annual resolution is actually quite little. So this is what is available now in INCAL. The blue parts were measured in annual resolution. So it's relatively little, but we have covered the first 1,000 years. We actually have also in the late glacial time, we have actually also annual resolution. When we go that far back, there is little chance to see the 11-year cycles because a lot of the C14 decayed. But we now analyzed quite a bit more. This is the part that we analyzed now. So we more than doubled the annual C14 measurement, and we can now have a closer look into the past. When we analyzed this, we had a nice introduction to the wavelets. So this is a wavelet plot of the whole data set, and you see, of course, we have some gaps still, but what we see is that we probably can see here on this slide the 11-year cycles. But now I would like to pick out a few examples. So we had in our paper about the last 1,000 years, we had in orange analyzed these peaks, the Spur and Maunder minima. So what I would like is to actually pick out some other solar minima, but I've chosen to take the Hallstatt, after the Hallstatt plateau, a solar minima, and at the time of Ötzi, also another solar minima, and we'll have a closer look on those two now. So here you see on top again what we have measured in the tree rings, and you see this strong increase, what indicates a solar minima. If you do then the analysis again, then we see that we have nice 11-year cycles before, that's in the Hallstatt plateau, and then when the solar minima comes, these wiggles, they seem to pretty much disappear before they actually appear again. So here I would say you can nicely see this transition from 11-year cycles into no and then back again. It looks about similar when we go further back in time, at the time of Ötzi. We see again very nice wiggles, and then solar minima, and then wiggles again. And in principle, this is a little bit astonishing because here at this time, what we measure is only half of the C14. So it's much more difficult in principle to detect the 11-year cycles. We did then analysis during minima and maxima, what are the amplitudes, and this is a kind of a slightly different analysis we have done now. What you see is with the 2 sigma uncertainties, the peaks, how large the amplitudes are, in green during solar maxima, and in orange during minima, and the blue is both together. So this is for the last millennia, and we know it's about 0.8 per mil. So when we now do the same analysis for the other 2 solar minima, then we see that the picture 2,000 years ago look quite similar. Maybe the amplitudes are slightly bigger actually. When we go then to the time of Ötzi, then we clearly see that the amplitudes are really bigger, and therefore we can see them still very well, even though we have much less C14 to be measured. Now we can look at these relative numbers, and I would just take this then as an idea to look at the strength of the Earth's magnetic field, whether this is actually correlates really with the Earth's magnetic field. When we look what we had over the last 1,000 years, we can look what was the dipole moment. When we then go for 2,000 years ago, the Hallstatt plateau, then we would expect something similar, maybe slightly higher. If you look at the heights of the 11-year peaks, then we would say it should be maybe slightly lower, but it's, I would say, in very well agreement. Also acknowledging that we actually have seem to have over this period a quite strong decrease in the Earth's magnetic field strength. When we go further back in time, as expected, that's again in the star, as expected, it's the dipole moment is much lower, so it's in good agreement. It's in good agreement, namely with the green curve now. So the two curves represent two different kind of Earth dipole moment reconstructions. So we think the Panafka reconstructions are better. It's also a newer publication. And that seems to fit quite well with our data. What I show here are actually the 14 zero records on top for the different periods, and you can see that the increase in C14 is always about quite similar, but if we now correct everything with the Earth's magnetic field, what turns out is that the Hallstatt and Ötzi minima, they seem to be quite a bit, the minima are higher than they were during the last 1,000 years, the Maunder and Spur minima. So the little ice age of Maunder and Spur minima seem to be an extremely strong solar minima, while the others are probably not as strong. And to come to this conclusion, I think it's supported by the heights of these 11-year cycles. So with this, I would like to come to a summary so we can see the 11-year cycles back over the 5,600 years, also because the Earth's magnetic field was eventually a bit weaker and allows us to see a bit more. But we have to admit that we can't always see the cycles during solar minima. And what is also seems to be the case is also that the grand solar minima seem to be now different at different times. So the sun didn't do always exactly the same as it looks like. With this, I would like to come to an outlook. So far, there were very little annual resolved data in INCAL. In the future, there will be much more. We more than doubled the C14 measurements over the 5,600 years. There is now only a gap of about 1,000 years missing that we have to analyze, and then we have a full, complete record for this time. With this, I would like to end. Please, if you have questions.
No singing now? Oh, where's our little choir? Oh, nobody. Okay, so I can see a few hands raised, maybe Elisabetta. Sorry, I didn't. Okay, so Alex, sorry.
About 40 years ago, it was done work by Burchuladze in Povinets, about 11 years sun cycles based on cognac spirits for the last 350 years about. Did you try to compare these results with yours?
This is Russian record from Russia, you mean?
No, it's Georgia, former Soviet Union.
Yeah, I think I'm not absolutely sure if you mean the same, but there is one record that does not agree at all with ours, that showed extreme 11-year cycles that are as such not true, in my opinion.
Because in Georgia they have a nice collection of cognac spirits for 300 years, more than 300 years. They measured them by liquid scintillation and gas proportional in the Czech Republic and in Soviet Union.
I personally don't believe in this data because they have amplitudes that are maybe 3-4 times as much as we see, and also the cycles don't quite precisely agree. But I mean, I don't know why those trees should be behaving so differently. This is all I can say.
There is no comparison, right?
No, I did once for myself compare them, and they didn't compare that well.
No, that will be interesting.
Yeah.
Three rings with...
Yeah, but as I said, I mean, it's not a good comparison, and
Okay.
This talk is about something different.
Yeah, regarding the geomagnetic field closer to the Hallstatt plateau, that is one of the cause of the difference in this plateau for the C14, if I understood correctly, of course. But there is a strong attempt now to use the intensity of the geomagnetic field locally, the local intensity as recorded in heated sediments, ovens, pottery, and so on, to use for dating. So can we integrate this with the C14 or the intensity?
Yeah, I never really thought about this in detail. If the combination, I mean, you are right that during the Hallstatt plateau, you can probably expect a decline in the Earth's, or an increase from the past, an increase in the Earth's magnetic field. And there might be maybe a chance that you could say a little bit where in the plateau you are. I think also our new remeasurements, they show that the plateau is maybe not that much of a plateau as we already thought, and I think still that with C14 you probably get a more precise result. I mean, and the local Earth magnetic field, this I don't know how much it tells you. So the values we are using for C14 are global. It's the dipole moment. So locally, the Earth's magnetic field might actually look quite different. So, but I'm not an expert in this.
Yeah, relating to the first question, where do the trees come from, which you are actually using? You have a whole set of tree rings.
So we used primarily trees from Europe, but also some trees were from the US. So we use also Bristol cones for the analysis. And they are maybe slightly offset, but that's not significant for our studies.
So the discrepancy with what he said cannot be explained in a way.
No, we could never see such discrepancies. We analyzed also already some Russian trees and from high Siberia. We couldn't see Yamal, and we could never see any difference basically. I think when you go far north, you might have a little bit, maybe 10-20% more signal, because there is less ocean probably, and then the signals appear a little bit stronger. There is a tendency that maybe you see this also on the events, that might be that you see changes a little bit better, but just in the order of 10-20% maybe.
Okay, thank you, Lucas, for the. Oh yes, come on. Oh, wake up, people. Now we have another. The conveners are switching.
So our next speaker is Quan Hua, who will tell us about methane from trees. I didn't know that trees are a big source of methane, but you probably will tell us more about that.
Good morning, everyone. You hear me well? Oh, sorry. Oh. It's not there. Okay, I'm still talking about trees, youth tree, but they emit the CH4 from the wetland, and then talking about the source and the age of that wetland CH4. Okay, you know that the CH4 is a potent greenhouse gas which have a global warming potential much higher than that of CO2. 87, 32, 11 times higher than CO2 at the time frame of 20, 100, and 500 years respectively. And that diagram shows you the warming effect of the greenhouse gas for a recent period of time. And you can see the second largest contribution, it comes from CH4 from the light green, just after the CO2. The global methane budget between 2008 and 2017 show a diagram showing the source, natural source of CH4 in green and the anthropogenic source in orange. And the biggest source of natural source is wetland. They contribute about 40 to 70% of the natural source of CH4 based on the bottom-up and the top-down, estimate respectively. And the current wetland CH4 study have been focused on the diffuse flux, that's been from sediment, from aquatic, and just in the last decade or so, it has been shown tree can emit CH4. And you can see here some of the three examples of the paper I showed there. And the tree methane emission from tree stem attract growing attention because they can account up to about 50% of Amazon basin CH4 budget. However, the source and the age of that emission have been resolved yet. And we have studied the source and the age of the tree stem CH4 from a coastal subtropical ephemeral freshwater wetland with intermittent flooding in the side in the northern of New South Wales in Australia. You can see there. And the site is, like most of the tree there is the broadleaf paper pine wood capable of emitting some of the highest reported CH4 today. And the forest is about 40 to 50 years. And they have three different field trip campaign to collect the sample. The first one in July 2022, focusing in the transition and upper zone. You can see the side on the left-hand side. And the second one in the transition zone in the February 2023. And the last one in the last year in May, okay? And what we collected, we collect the tree stem gas using a chamber, small chamber, firmly connecting to the tree with the help of the O-ring. And you can see the chamber connecting to the one of the custom order 1 liter of carbon foil bag. They have some of nitrogen gas there, and during 24 hours, the gas emitted from the methane from the tree, and that's one equilibrated. And we used the air pump to improve the gas circulation. And we also collect the pollution bubble from the sediment by disturbing, because they're not the continuous flux. We have tried to help to collect the gas. And the gas was trapped using the funnel trap, and you can see the syringe, and then after that, put into the foil. And this thing here, we put the 14 CH4 to emphasize what we're doing, but actually, they own the gas. Not only CH4, own the gas there. Okay, and other thing is the soil, profile from the top to about 50 centimeter depth. Okay, and here at the bottom you can see a typical concentration of the gas species in the collected gas. And most of the three-stem CH4 mainly is CH4 and CO2. And you can see at the lower stem, about 25 centimeter high, you have a 1600 ppm of CH4 and 12,000 ppm of CO2. Higher, at the 140 centimeters, you have 200 ppm of CH4 and 5,000 ppm of CO2. And other gas like CO and volatile organic carbon is very low at the pp level for the VOC and just 1 to 8, ppm for CO. That means most of the gas is CH4 and CO. And here is the line we use to extract or separation CH4 and C2. As you can see, to start with the gas sample bag, and then we have a water trap I cannot show here. Okay, the water trap to collect the water and most of the VOC. And if the VOC is trapped there, you can collect in the water trap here with liquid nitrogen. And the CO2 collected here as well. And on the CO, convert to the CO2 by the Sopno-Cap reaction at room temperatures. And finally, collecting here. Only one gas go through is the CH4 not condensed by liquid nitrogen and reaching the furnace here containing of the platinumized quark wool, and the CH4 was converted to CO2 at 750 degrees and collected in the liquid nitrogen here. That means two fraction, CO2 fraction and CH4 derived CO2 fraction were collected for characterization and MS analysis. And they have some experiment carried out to try to optimize the extraction and see mainly on the flow rate and how many traps we need for each stage here. And we found one trap for liquid for CO2 not enough, have to have a two. And the higher flow rate, they can put a lot of pressure on the upstream. And the result of the high flow rate and the one trap for CO2 can get some of CO2 breakthrough go to here. That's happened for the first pilot, the pilot and the first trip sample. And we only found some CO2 were partially absorbed in the solar cap. Okay, and then that is the line. You can see on the picture, and you can see the sample bag, solar cap here, the furnace down there, and the quadruple mass spectrometer for residual gas analysis. Okay, now we have a total of 82 gas fraction and the soil organic matter, and mostly contained in the range of 12 microgram to 10 milligram, and about 70% of sample contain less than 100 microgram. And we use that the micro furnace, the hydrogen and ion method, and the lowest volume is 0.9 mil, including the pressure transducer. And for a larger sample, we're just changing the volume of the cold finger to handle the larger sample. And on the sample measure in Antares, and the MS analysis of micro sample, I will advertise to my colleague Andrew Smith will talk about that more in detail on Thursday, session A1 at 2 p.m. Okay, now the result. I showed that one a different batch. You can see the CO2 and 3CH4 in blue and red, respectively, and evolution CO2, evolution CH4, and solid matter in gray. And as I mentioned before, in the first pilot study, we got a problem with the CO breakthrough, and on the CH4 are not reliable because they get the CO2 through. Okay, and then we found some of the data, his A2 and A12 had a problem when we extracted and not completely, transfer. And we got a problem. And then one of the sample here, A17, have the gas leak, and These data also remove it. Okay, now if we put that one in block box, you can see blue for CO2 fraction and red for the CH4 fraction. The PMC value of the CO2 is similar to the CH4, although they're more variable. Okay, and the most of the content is about 95 to 100 PFC, and that's similar to here is the soil organic matter, the average value about 10 centimeter depth at 100 PMC. Okay, and the blue line atmospheric level is the contemporaneous carbon-14 for during the time we study, and based on the information from Jocelyn Turnbull from GNS. And the red line is the contemporaneous atmospheric CH4. They measure about 135 PMC in 2000. And you can see here is the evolution of the 14 CH4 reconstructed from the ice core, from the polar ice and firn. You can see the high level of CH4 due to the power plant industry. Okay. Oh, sorry. You can see the methane CH4 is close to the atmospheric carbon-14, but much lower than atmospheric CH4. And if we put everything to try to the looking for the source of CH4, we use the cooling plot. That means we plot this carbon-14 level over the 1 over the concentration. You can see here, and that's one for the trip number 2, that's one for trip number 3. You can see, except for that one, the other one, you can see the cooling plot point to what the source is the evolution, where, the small dot is the tree stem. The larger one is evolution. Sorry, I mentioned. Okay, then where the higher concentration of the CH4 or CO2, where it is sourced. And now I put everything into the diagram. As you can see that on average value, the highest concentration of evolution is about 2.1%. Then it's gone up smaller for the lower stem at 1700, and then to 39 ppm, right? At the same time, you can see the carbon-14 of the lower evolution and the soil is similar. That's telling you the study 3, MSCH4, derived from young soil carbon. And this was supported by other work previously on Lecce carbon-13. You can see the evolution and the carbon-13 from the lower stem is similar for different species here. Okay? And then, to summarize, that's one of our field campaign. Then the carbon dioxide get into the tree by fixation, and we know, like Lucas mentioned about carbon-14 in the tree ring, right? But some of the carbon dioxide there get into the root, then fit into the soil. And in the soil, in the same way, the CO2 and the CH4 somehow go back from the root, going up, maybe from, like the nutrient way, going up, and it emitted the CH4 and CO2 under the bark. And our data, that species is not have a deep root, it was quite shallow, but they have some vertical root going down to reach the level of the water, to get the water. But because of it's a flooding area, most of the side is a flooding, and that's why the root not going that deep, and that's why maybe they just get, the shallow soil and sediment. That's why we have the soil is quite young carbon. And I would like to acknowledge my collaborator, is Luke Jeffrey and Damien Meher from Southern Cross University for collecting the sample. My colleague from ANSTO, Andrew Smith, did process the gas sample and mass management, and Bin Yang did a lot of most of the graphitization. And would like to thank the funding from ANSI and from ANSTO. And thank you for your attention.
Thank you.
Yeah, thank you very much for this nice presentation. I was actually wondering a bit, are you sometimes influenced by the methane background? I mean, the methane has typically a very high C14 signature in the atmosphere. Did you ever measure that? And are sometimes your results influenced by that or not?
No, I don't think. That was showing.
Because the concentrations are so high,
no,
then.
It's so high. Yeah.
But you never measured
It's so high, yeah.
You never measured the methane in the atmosphere on the southern hemisphere too.
Yeah, they have some data. I show you from the Hamish Sheffer measure and the polar.
But you didn't measure yourself, huh?
No. Okay.
So.
I just wondered, you show that atmospheric methane at Bering Head is about 134.
What I say again?
Atmospheric methane at Bering Head is 134% of matter.
Yeah.
What is the explanation for that? It's actually quite old. That means this methane formated from organic matter which was growing. What?
Is it you asked me why the high level of
1970.
methane? Because of the power plant industry, because the more popular, like pressurized pressurized water reactor, they emit, CH4 and the carbon 14 from CH4. It's the most popular, that's why they contribute very high of atmospheric CH4.
We did something similar in South Carolina, but only CO2. We did not do methane, and we find out that actually all the CO2 is about 3.5 meters, and its gas activity is about 130% as well.
Okay, thank you.
I'm just wondering, does the tree use methane at all, or is it just passing through? And
they passing through. And the thing is, what I learned is on tree, they emit CH4. But in the highland, when you have well drain, then, but in lowland here, you have flooding, you have anoxic, condition. And that's why the bacteria produce a lot of CH4. And in highland, they still emit the CH4, but in at least one or two other fraction less than of the wetland. And the tree just using as the channel going up.
Yeah.
And we have another project, from PhD, and what we call is the dead forest, we call it ghost forest. They die, but they still emit the CH4. Okay, and the PhD student will come and we will working on that next year, right? Yeah, next year, yeah.
Okay. Maybe a very quick question from Guasiara, and then we continue.
Great talk. Just following up on what Walter was saying, in this forest, you tested just 1 tree species, or was a lot of tree species? And if all of them behave in the same way, is there some kind of adaptation for this type of trees in these wetlands?
You mean
Did you test a lot of tree species, or is a particular tree species that behave in that way?
Okay, they have a different species. You can see another side of the species here. The species I use is the most of the highest, CST flux. The other species is smaller. I show one of but now you have much lower, the CH4 flux. Because maybe of the physiology of the species or something. I'm not in that expert to mention to you, but it depends on species. But the one we want to choose because we know they have the highest, and that's easy for us to start with. Yeah.
Okay, thank you.
Thank you once again, and we will continue now with Elisabetta Guaretto. She will tell us what the trees from Israel can tell us, I guess.
Can I have the banner? Sorry. No, but you don't have the pointers. I hope that the mouse is more... yeah, but do you see the pointer? Okay, thank you very much. So I'm really having great information out of this session, I would say, because we have several problems with the trees in Israel. So here we are. So this is Puglia. Can you see the mouse? Yeah. This is Puglia, and we are a little bit more south with different kind of colors somehow, but still a lot of green. And the important things that I want to make you note in this map is that while Puglia has, the lowest rain precipitation per year is about 500 millimeter per year, and you have your red zone, we have a much more red zone, and actually we have a much more location with less than 500 millimeter per year, it's a real desert. But the major point in these maps is that this boundary, you see this boundary between the desert towards the more Mediterranean vegetation are very thin. And so they represent a beautiful opportunity to study paleoclimate, because if in the past there was a change in the precipitation, then this boundary will definitely move north or south in a very short time. And this was the major point that we wanted to study with the tree rings, because we have stalagmite, but stalagmite are very rare, and we thought that the tree rings could be a better archive. Indeed, if you take the Pinus, the Pinus alepensis, which is a recent addition to the area, or the oak, the Quercus itaburensis, which is more local, you see a very good agreement between the width of the ring in blue and the precipitation. So more precipitation, bigger ring. So this is very nice because the tree respond to the precipitation very nicely. But so we have only few trees, and but we have many other trees that are more local in the Near East. Acacia, pistacia, cedar, juniper. So several trees. And we were wondering if we can use some of them beside the oak and the pine, which the pine you don't find in the archaeological record, to study the paleoclimate. So, but the first question is, do they produce annual ring, these trees, that we can measure and maybe find? So, first of all, is the first question. Second problem we have is that in the Near East, we don't have many very old trees like you are very lucky in Europe to have, you can see, thousands and thousands of years of dendrochronology. We don't have this, and that's why you have to go to the archaeological record and study the charred remains from wood, of course, trees. And indeed, by excavating, when I was excavating sites in the Natufian period, like 10,000 to 14,000 years old, or the Manot Cave, which is from 50,000 down to 30,000. So we were very lucky to see that, after all, the composition of the charred remains, as identified in the botany, are present day also trees. Not all of them, like we don't have much olive, for example, in this record, in the 10,000 year record, but we have oak, we have amygdalus, which is the almonds. And also in the Manot Cave, which is, you see, from 47,000 years down to 33,000. The almonds is almost the major tree that was used to produce fire, which give you a lot of insights also in the forest, which was around the Manot cave. So we decided to use this amygdalus, which is a short-lived tree, something like 100 years. So the old wood effect, is not important for the chronology that we were investigating. And we say, well, let's use this amygdalus, which is with us in the Near East for a very long time. And just a small curiosity, in Hebrew, amygdalus is called sheked, which comes from the verb lishkod from the Bible, which means persistent. It's a tree that is the first one to bloom. It has an holidays for him, a fest, and is persistent. No matter what, I'll be here. So this is the word sheked. And therefore, we used, because these are charred remains, very small, so no dendrochronology is possible to do. So to use the fractionation that happened during the, during the photosynthesis, this amazing chemistry that allowed us to survive in this planet. And because if you have a very good condition, in the precipitation, then the stomata will remain open, and the tree can do the selection, the fractionation of the carbon isotopes, while if you are in a very dry regime, the stomata will close and then no fractionation will take place inside the leaves stomata, and all the isotopes will be used for the photosynthesis. So, say that, so this is the rules for the delta C13, and these are, the big delta C13, which is from the Farquhar, and it put in relation the stable isotopes of carbon with the rain, the precipitation that the plant have seen. And so this is the Manot cave in the north, and in red are the Natufian sites we have studied. So we are facing the Mediterranean, and by measuring the stable isotopes, that's for you, ion plus, and measuring in the modern trees, of course, we tested the modern trees, the dendrochronology, measuring with the C14, so we know exactly what the time was, the excavation, the almonds is here blooming. We build up, here is time, calibrated BP, and these are the big delta, the stable isotopes of carbon, and we go from dry to wet. And you see that the almonds from 50,000, 40,000, we had variation, but still a nice group of wet condition, but also very dry condition for the almonds, even dry that today. This gray band show you the today stable isotopes in almonds that we know how much precipitation they received. So we were, in this period, even more dry, but still the almonds survive. This period, you see, no almonds. We never found so far sites with almonds. And then it reappears with the younger dryas, and we were very wet here at the onset of the agricultural revolution. So very nice. And we were surprised that we don't have anything here. Also, the sites are not, the archaeological sites are really very rare in this period to be detected and chronologically dated. Luckily, we found one site that covered this period from 20 to 26,000, but with oak. The tree ring that was used for fire was oak and not almonds, something that we are investigating why almonds disappeared, being so ubiquitous during these periods. But the oak is not so sensitive to the precipitation. It can survive and do the fractionation, although the condition, the precipitation is different. So it wouldn't be our preferred tree. So while the almonds seems to be much more sensitive to that, so a better archive for precipitation. And we compare also with the stalagmite, and we see that, the almonds, the red triangles do follow the delta 018 of the stalagmite with more rain or less wet condition. So, okay. Coming from Israel, I'm a little bit sensitive. Sorry. No drone outside. So, sorry for that. Other trees are available. We saw that we have juniper and so on. And to our so we decided to go for the acacia and the pistachia, the olive we did already in, so 10 minutes less I have, or is counting down this one, or is counting up? It's counting down.
It's counting down, but you have a little bit less than indicated.
Ah, okay, okay, you tell me. Okay.
Maybe 5 minutes, a little bit more.
Okay, so I can go slower. No, because this boom. So, the acacia and the pistachia, because these are more common, and the acacia, which in Israel we have the Nordest acacia, Acacia albina, that can survive at a high latitude. So we have a lot of acacia in the desert, which would be this boundary that we wanted to check if the precipitation in the past has changed dramatically. And pistachia was a tree which is more often found in the forest in Israel. So acacia is beautiful. I mean, it has a pattern which is fantastic, but it's a pain in the neck. Now, these are the years here, from 1955 to 2015, when we cut the acacia. The boundary between these different colors are determined by C14. We took a sample and we dated with C14, so bone peak is pretty much precise, not much mistake. And the number inside here is what has been counted by dendrochronology. And you can see that, for example, here, between this boundary and this one, the dendrochronologists count 9 rings. But actually, we have 5, 10, almost 15 years counted by C14. So C14 say, no, you have more time and you don't see the rings. And even in this case, we have 15, almost 20 years by C14 and only 14 rings, which is a little bit too much as a mistake, as a missing rings if you want to do dendrochronology. So this acacia is difficult. You see here a close-up. It seems, you know, that these are the rings, but we need, because there is this disagreement between dendro and radiocarbon, we need another way to, independent, to figure out if this tree does indeed 3 rings annually. And so we use the scanning microscopy to do that, and we approach this acacia radiana using you see this white line? These are deposits of oxalate. And we thought that these are marking the early wood, the late wood, the dormant period, because we are in the desert, and the tree receives the water only in the winter and only when the river is flooded with the water. So you see these rings, so we thought, okay, let's use this oxalate as we see clearly in the SEM to mark years. And so now this is another attempt for this acacia, and these are 2008, 2009 are years determined by C14. So we took a sample, we measured the C14, and these are the 1991 and 1993. So you see, and these 53, 47, and 40 are the dendro rings from the ring number 1 in the center to the last one. So between 47 to 53, you have 6 dendro rings. From 40 to 47, you have 7 dendro rings. And by C14, you have 16 years, or more than 35, because this is before 1955. So there is a disagreement. If we use the oxalate bands, then in this period we have 6 oxalate bands, 6 dendro, and 16 years by C14. And here we have 26 oxalate bands, 7 dendro rings, and 35 rings. 35 years, more than 35 by C14. So total chaos, disagreement between everything. So the pistachia has the same problem. We can't figure out, even if you see beautiful pattern, you can't figure out here who is the real ring, the early wood, the late wood, when it starts, when it's dormant. So we gave up on pistachia, but as an archive for precipitation, but we had this, we published several papers on the olive and the pine, the Pinus alepensis and the olive, that live just 1 meter from the other. They are exactly in the same forest. And by cutting early and late wood, something similar to what Susanna and Lucas did in their last paper. So we tried to see if actually during the bomb peak the pine grows as it is expected, or if fit the northern hemisphere 1 bomb peak curve, the blue one or the red one. We should be in the red one. Israel is a lower latitude. We should fit the red one, but actually our determination of C14 in the early, which is this pinkish, is the pinkish, this pinkish band, and the green one is the late wood. According to our C14, we fit better the North Hemisphere 1 bomb peak curve. So, and just to tell you, the pine, for example, grows twice in the year. It doesn't do 2 rings like the Cypressus, but it starts, for example, you see in the spring, it does a very short, very small period of growth, early wood. Then it has a late wood in the summer, but then when you have the hottest month, the pine goes to sleep, and it starts again in the autumn to do another early wood. Doesn't mean that it's large, that it's short, but more early wood. So, and together with that, we put the yellow triangles are the olive tree that we measure, and we see that the olive tree just decides by himself when to grow. It can grow in the spring down to the middle of the summer. It can grow in the winter only, so it's very rare. But when we published this one, we didn't see your last paper, which just came out now. You see 00000 in radiocarbon just last week. And as usual, you prepare your talk, and then poof, a new paper comes up. And you found, and Susanne is here, and Lucas is here, so you can ask a question to them, they found that the tree in your location actually use some old, like 2 years before, carbon, and reuse it to make, in the spring, when it starts to grow, part of the, because if you don't have leaves, how do you bloom, for example? You need some carbon out of it. So anyway, so this has raised for me a lot of questions, and I think we are going to investigate again our results to better understand if we are indeed correct in our conclusion. So I'm coming to the conclusion, and I think that by using the charred archaeological remains, which are very small, millimeter size sometimes, but we can measure the stable isotopes of carbon, date the material, and in this case, use as a parameter to reconstruct all the precipitation and maybe climate and environment. But not all the trees are suitable for this archive. And indeed, we did a lot of work on the modern trees. We char them, we measure the fractionation by charring, and also if the stable isotopes and the dates are indeed suitable for this. I think that the integration of dendrochronology, radiocarbon, the stable isotopes, biomineral that you can find inside the trees might give you more information that certainly beyond the studies of the paleoclimate, we are very much interested to understand how this acacia, how this pistacia indeed does the photosynthesis, and take these C14 and stable isotopes in their trunk to understand if by measuring, as we did with olive, continuously the C14 in a core, then really figure out how these tree biologically survive climate change that is present. We have a large variation also today of rain. So I think that these are all the collaborators that helped me. 2 Italians, by the way, from Lecce. One from Napoli, Valentina is from Lecce, one of your scholars, and Chiara is also from Napoli. So Italians have indeed contribute a lot to this research. Thank you very much. Nessun dorma, tu pure principessa, nella tua fredda stanza, ma il mio segreto è chiuso in me. Basta.
Yeah, thank you very much for the nice presentation and for the advertisement for us.
I wanted to change this volare.
So we have just time for one quick question. Chiara? Yeah.
Can we go back to the slide that you showed, the olive trees date? Because you mentioned that you didn't know exactly when they were going, spring or other times. How actually you plotted the dendro years or actual calendar years against the current 14 data, if you do not quite know when they were grown, go backwards?
Here it is. So this is what we published in another paper. This is the bomb peak.
Yes.
You see? Yeah.
But how you determine the actual calendar, the dendro years or the actual calendar years to plot it so you have a big range?
Well, because you see, indeed, we had more than some solution. If you measure only C14, you can have more than a solution, except for this year, you see 64, which we have something like 12 measurement in continuous, because we took the core of the olive tree and we just cut 20 milligram consecutively, and we measure the C14. And the other fact is that with the stable isotopes, you see when it's dormant, and then it starts to grow, and then you have a very big change in delta C13. This is when it goes dormant, the olive tree. And the delta C13 has been actually very useful to figure out the different years. And so we could then plot the C14 more precisely on the bomb peak. It is an integration of the stable isotopes with the C14.
Oh, okay. Okay, thank you.
I think we have to continue now with Matthias Huls, who will present us the dual isotope approach, right?
Oops. Thank you very much. Where are we? No. Okay. During the last Radiocarbon and Environment Conference, I presented the radiocarbon measurements done on wheat samples, which we collected from the Garterslehm Plant Crop Institute. and that was in 2021. So the results were going to 2020. Today, I would like to present an updated version of this by continuing this to the last year, 2023, and also including soybean to this record, which will grow slightly different from the wheat in late summer. So this is a map where the Gartersleben Institute is located. It's located between the city of Magdeburg and the Harz Mountain in a rural area, mostly dominated by agriculture. The Leibniz Institute for Plant Genetics and Crop Plant Research is one of the world's leading international institutions in the field of genetics and crop science, and hold lots of different plant species and crops. One of the co-authors gave us the opportunity to get access to the archives, and this is what I'm going to present today. So the idea of sampling came when we start studying the possibility of dating paper. So the wheat samples consist both of the winter and spring growth habits. That means the winter seed is sown in October, and it starts to grow between April and July, harvested in July. Whereas the spring habit is sown in April, depending on the weather conditions, and harvested in late July, early August. Soybean, on the other hand, is sown in April and harvested at the end of September, beginning of October. So both different crops collect carbon, which is metabolized from different or slightly different seasons, one from the early summer, late spring, which is the wheat samples, and the soy from the late summer. So what we did is we took the samples and principally just defatted the material, washed it slightly, dried it, have frozen it in liquid nitrogen, and homogenized the sample material by powdering. For each sample, for each season, we measured at least 2 samples, at least 2 subsamples. So material was sealed in closed quartz tubes together with copper oxide, combusted to CO2, graphitized, and then measured in our high voltage 3MV machine, which is already now 30 years old, and unfortunately lately became also broken. So we don't know whether we can fix it, but hopefully we can. This is the updated version. The record in green shown is the material, the C14 in the wheat samples, and the brownish one gives the C14 of soybean. I also give the atmospheric Schauinsland and Wermut record and the Northern Hemisphere Zone 1. And as can be seen, this plant tissue nicely record the radiocarbon excursions over the period of the bomb spike, starting to increase in around 1995 up to the maximum in 1963. And after the limited test ban treaty, it started to decrease, and recently we reached the radiocarbon concentration of 1. We became also interested in comparing to other available records over the bomb spike from plant tissues, and just recently Dunbar and colleagues published records from barley, which they have collected from the Rothamsted Research Institution. and they give radiocarbon measurements on barley in a 3-year resolution from 1852 up to 2020. And last year, colleagues in the US have published radiocarbon measurements done on annual plant grown on the Colorado Plateau that they included in their measurement samples from 1910 up to 2020. This is the comparison between the Gattersleben plants, which are shown in green or in green crosses. In blue is given the barley radiocarbon concentration, and the red triangles gives the annual plants radiocarbon concentration measured in the plants of the Colorado Plateau. All of them closely follow as expected, the northern hemisphere zones 1 and 2 for the Colorado because of their more southern location. They should more follow the northern hemisphere zone 2. In detail, what can be seen is that for all samples before 1955, that they give radiocarbon concentrations which actually are below the reference files given, and also the INCAL 20. After the increase in above-ground nuclear tests, the radiocarbon concentrations increase, of course, up to the maximum seen for barley and Gattersleben plants in 1963, and for the Colorado Plateau in 1964. After the limited test ban treaty, the radiocarbon concentration started to decrease. Between 1970 and 2000, interestingly, the barley samples show slightly increased and more active radiocarbon concentrations than the other plant tissues, as well as the reference database. The reason for that, at the moment, I don't understand, and I think also the authors have no explanation yet. Another slightly more active period is also seen between 2005 and 2015 in the barley, whereas the Gattersleben as well as the Colorado Plateau give just about or slightly below radiocarbon concentrations than the Northern Hemisphere Zone 1 and 2. And the recent radiocarbon measurements from 2023 are just about 1, or when corrected for the decay of the standard, slightly below 0 per mil. We also were interested in stable isotope measurements, which have been done also by the colleagues in England from Dunbar. They have done the measurements in the barley seed, and we have done stable isotope measurements in the wheat. And as can be seen, similar to the observations done by the colleagues in England, there is a constant decrease in C13 concentration in the plant tissues, which somehow got accelerated pretty much after 1995. But it seems also that there is some sort of a leveling off after 2015. We have to see whether this is continuing or not. The decrease rates given here are just a visual fit and not coming from any computational calculations. So this just for understanding. We also calculated the large delta 13C as the C13 concentration in the plant tissues is coming from the CO2 in the atmosphere and modulated by photosynthetic processes as well as environmental processes. So I was just curious whether there is any relation seen with local environment, and fortunately in Gaterslehm there's also a nearby weather station which provides data for precipitation as well as temperature. So first shown here is the local precipitation during the growth season between April and July. So just visually it seems as if there are only little variability related to the delta 13C. The plot sizes where the wheat is grown is only rarely watered. Usually it just takes the natural watering, and only during very severe droughts or strong heat periods it is watered. But what can be seen is a slight increase after 1995 in the delta 13C, which seems to be related also to an increasing temperature 2 meters above during the period between April, May, June, July. So there's not more I can talk about. And this is all. Thank you for your patience and attention. So, volare, oh, cantare, oh. Okay.
Thank you very much for your talk. Are there any questions? Yes, please.
Thank you. Doesn't work. So it works. I was wondering how much of the magnitude of the signal can be attributed to the genetic selection of the line. Even if you stay with the same species, in the 90s it was a period where there is a huge selection of some specific lines with specific phenotype. And I was wondering if you had a look at that point or not.
Are you talking about the relation between the delta 13C and precipitation or temperature? I mean, the results I just got last week, and I just had a very brief look and didn't look more detailed into it, neither with a correlation analysis nor anything more like what have we presented earlier on, whether there is some small modulation which can be correlated to these environmental changes. Overall, the large delta 13C seem to indicate quite some sufficient watering or availability of moisture.
Yes, another question.
Not a question, but a comment, because you are talking about genetic changes in the species they grow. But if there is any, you will see it only one species, and we have. Okay, but then in the 80s you see this decline in C13, both in barley and in wheat. So
yes. This is true, although there also could be seen some offset, which I think is related to some species-specific vital effects.
Matthias, can you go back? Can I talk?
Yeah,
Matthias,
sure.
Can you go back to the plot of the delta, big delta? Is one of the So the blue points are the big delta that you measured.
Well, the blue points here is just the big delta measured in wheat, so in the seed. And the black line is just a running mean, a 5-point running mean, in
but,
order to get some...
But the point you located like 1960, you have a blue point very close to the... this is 1 point per year. Sorry, I misunderstood at the time.
Sorry,
scale.
it's only 1 point per year.
Sorry. It's not.
No, all good, all fine.
Thank you.
So I think we stop here and we go to the final presentation given by Martin Seiler, who also uses the C14 bump spike to look a little bit what the trees are doing, I guess, and so on. So please, it's yours.
Yeah, so welcome to my talk about the C14 bomb spike and how we can use it to determine where the carbon is actually coming from. So first a little overview about on my talk. I'll first give an introduction. This is basically where we stopped, or my colleagues stopped the presentation in the last Radiocarbon in the Environment Conference. It was held online. And then I'll go into the biospheric carbon modeling that we did for further analysis, and then what effect that has on the tree ring measurements that we did, and then come to some conclusions. So first, introduction. So this was data that was presented in the last conference. We basically measured incremental tree rings in a pine tree close to Trondheim from basically the height of the bomb peak. We remeasured the samples from the Sitka spruce that was originally measured by Grotes et al. In the 80s. And we also reanalyzed data from Kane et al., which was an oak from Oregon. And yeah, what we basically see there is that all of these data sets, they show apparent delay, especially in 1963, compared to the atmospheric curves. And yeah, we see that it's not really a delay, but maybe also just lower values. So, which basically goes only for 63 if the growth period is wrong, but as we can see, especially here in the Trondheim 64, the maximum quite matches, so it just seems to be less C14 basically in the tree rings compared to the atmospheric data that we have. And yeah, one thing could be like a biological delay, that we are actually not getting the carbon quickly enough from the atmosphere to the actual tree stem, because there's of course some chemical reactions involved. But again, since the peak here is basically on the same time, we don't think this is the main problem. So what we think, it's basically the CO2 source. We are not getting the clean atmosphere into our trees. And of course, local atmosphere is known already quite well. Copied a little part of the article by Levine and Kromer 2004, where they compare the basically low-level data from Schauinsland compared to the clean air from Jungfraujoch with a significant difference. And so this is what I would call regional atmosphere. And then we have local differences. It is basically just within the tree. So where the canopy basically isolates the free atmosphere above from the more biospherically dominated part below. And as you can see in this photo from the tree actually in Trondheim, it's not completely dense, at least not in this forest, but there's some hindrance in airflow and so on. And yeah, to investigate basically what part of CO2 comes from the soil or from the trees itself, as we just heard from Kwan, and what part comes from the atmosphere, we basically need a difference between the two, or we cannot really see the change. And yeah, that's of course easiest when we have strong changes in atmospheric C14, such as for the bomb spike. And so the first thing that we started is trying to model this biospheric carbon. And of course we know we have some atmospheric data that we can start with. And then the first thing that we have to consider is that plants, well at least in Norway where we took the samples, don't grow in winter because everything is frozen. So we need to consider a growth period. And then later on we also have decay times for this organic material that lies on the soil. and of course different material has different decay times, so we add up basically old carbon, old only a few years basically in this time, but that will contribute basically old carbon there as well. And so the first step, we can just basically define our growth period and see what CO2 we would expect. So the green one here is what we think is most reliable, at least for the Trondheim, so middle Norway region, April to August. And you see the green points, they align relatively well with the Nipolomice data by Rakowski et al., which is also a pine tree. And I mean, there's some differences in some years, but overall we get a relatively good match. And also we just tried another longer growth period from March to September, and we see that there's more difference. So we generally think it's not that critical because lots of the values are quite similar. But of course, the critical ones are here in 62, 64, where we really have the highest, or strongest, fastest changes. And you also see another tree plotted here in blue. This is acacia. So it's different tree, and we see quite a lot of difference there as well, which can both be biological effects from the tree, but also the difference because of course it's further south in Hungary. The next thing is then when you have all the biological material, the tree itself hopefully stays alive, but of course we have needles from the trees that fall eventually. We have small shrubs and mosses that more or less annual life cycles or quite short lifetimes overall. And so we basically defined two sets of litter based on this article from Hilly et al. One for pine and one for oak, which is of course then related to the oak tree from Kane et al. And the main difference is that there's a lot more leaves from the tree because they fall every year compared to needles that live several years, and also that the leaves normally decay a little bit faster. And for checking, we also had old and young litter with basically single-year decay time, or with a 50-year decay time, we will have very old things. The problem here is that we did not really have samples for checking, so this is a little bit going theoretical for the moment. But we can, of course, calculate whatever we want. And so this is just the model of the bomb curve, the NH1, which is relevant for us. And we see with the old litter, there's barely any change, because, of course, there's very old material still decaying. While, of course, with the young, we more or less follow the bomb curve with 1 year delay. And, of course, our realistic assumptions for actual litter are somehow in between. Now, what's the effect for that on tree rings? First, basically we can just model whatever mix of atmospheric and this biospheric C14 to get in our model. But how much do we actually need? And of course, we need a large difference to get some accuracy for the modeling, which of course is why we use the bomb spike. And so this is basically the blue data points here, our measurement data from the tree in Trondheim, compared to the NH1 curve. And we can already see that some data points, especially here in 64, but also the end of 62 here, we are actually above the NH1 curve. So that's why we do not use this one for this tree, but actually a local curve compiled of atmospheric measurements in Scandinavia, mainly Lindesnes and Fryholm, which is the longest data set with most points. And based on that, we can mix it with different fractions of biospheric, and we get basically this lower orange to red curves, depending on how much we allow for the old carbon. What we actually want to do is determine how much biospheric influence there actually is. So for each data point, we can basically calculate this value. And this is what we see here in this plot. So each data point over the bomb spike years, of course, there's now tree growth in winter, so we're missing those parts. We calculated the value of how much biospheric content there would be according to the data. The first thing, of course, is that we have some negative values here. that doesn't make sense in the model, so there must be something wrong. Either with the modeling itself, which we think is not really the case, because independent of what we add, or especially if young or old litter is used, we always get negative values. So it's likely that we are missing some part of the carbon structure, so another carbon source, or that just one of the data points is a little bit off. We see another one here is a little slightly negative as well. The other thing is that we see quite strong changes over the years, so especially here in the 62 year, we basically start with 0, we get an increase and a decrease towards the end of the year. Slightly different behavior in 63, where it seems to be decreasing, and a rather constant behavior in 64. So of course it's only one tree, so there can always be some local variations, but the main things that we think we have to consider that we actually can see in this, especially this peak shape, is that we have a change in decay rate, because early when tree growth starts, everything, or not everything, but things just start falling, so that the decomposition of litter will be very slow and just gets started with heating up and of course with biological activities rising. And this also causes either directly or indirectly a change in airflow rate. So of course with pine trees they still have their needles, but the canopy will get more dense, and with more vegetation going up, the airflow and the exchange between the sub-canopy air and the free atmosphere above will be hindered. So that's why we would expect a decrease or increase actually towards summer, where we have most activity. And yeah, we see some variations between the different years. So we are below 10%, then we get a little bit higher, and maybe back to about 5% for the 64 measurements again. So that would maybe indicate that the decay times are not quite correct, because of course the C14 values change quite a lot between that. So yeah, but first, before we want to correct anything that, we just look in other trees, and of course this is this Sitka spruce from Washington, northwestern United States. Here is just the data plotted the same again. More interesting would be the right side here, and here we see this inverse U shape basically in every year. So we get quite low biospheric content in the beginning, it rises later on in the year, and then goes down again towards the end. We see here also relatively constant values of about 10%, maybe 15 or so for 62 and 63, and then a little bit lower. Since we can see here, and basically the extreme case of very young litter, the values can go a lot higher, which would probably indicate that you're overestimating the turnover time, the decay time of the litter a little bit, so that these points would go higher up as well. And so this was also a spruce, so evergreen tree. Now the last example that we looked at was this oak from Oregon, and of course the big thing here is that oak is not an evergreen. And we see that, at least we think, mainly in the beginning of the year. We see very low measurement points in the beginning of the year, or high respectively. This is what we address through non-structural carbon from the previous year being stored and used up to build or start growth in the beginning of the year. And this leads to also somewhat high values here, especially in the beginning of the year, with also lots of variation. Of course, this is not considered in the model, so we don't really have to care about these values. Also, these are above 100%, which of course doesn't make sense. But then again, after this non-structural carbon has been probably not used up, but has been reduced in significance, we have quite similar effects, relatively constant biospheric contents over the year, quite low here. That can be also effect maybe of the local, so this is NH2, a little bit on the border, but officially in the NH2 region. So maybe the NH1 local curve would give a little bit higher values here, so that would match a little bit better as well. So these were the examples that we investigated so far. After that, I come to a conclusion that we usually have a quite significant contribution of about 10% of local biospheric CO2. And this needs to be considered especially when we're comparing tree rings and atmospheric data, since there's a difference there, and also if you want to look at different trees or different plants and different habitats as well, because not all might have the same contribution of biospheric content. And yeah, of course this is basically only relevant when it's fast and large changes in C14 currents, such as the bomb peak, maybe has some effect on Miyake events or similar rapid C14 changes over time. And with that, I want to thank you for your attention.
Volare, oh, cantare, oh.
Yeah, thank you, Martin, for the presentation. Are there questions? Yes, please.
Thank you very much for this very interesting talk. I have a few questions. The first is, how do you recognize the age of the litter? The second is about the litter of the pine, for example, young and old litters, because maybe I'm wrong. If we have the litter, there is no more photosynthesis. So how the carbon is collected or given to the air from the litter? And you said about the 6 years of the decay times. So this is what I found on the ground. How I can know what is the age of that? If it is 1 year, okay, this is a green, so I can estimate it. But then they start to be dry. So it is really, in my opinion, so I would like that you correct me, it is really difficult to say if it is a 6 years, for example, old, or it is 1, 2 years. And also, when we are working with the needles, usually if I want to stop the photosynthesis, I just take them into the labs, I dry it. So if my needles are dry, immediately after when I collect it, I finish photosynthesis. So how this process, the cycle of the carbon, is in the pine litters. Could you describe it, please?
Yeah, well, these values are basically described by this Hill et al. Article. They investigated, well, they collected litter, of course, a modern one, 2010. They can have been different, of course, in the 60s. And they basically measured, first, how much there is of different parts, basically. They had these raw categories that I took over here now. And they basically measured how much there is left after a certain time. So they basically checked how long the decay times are. They didn't specifically look for carbon only. Basically these decay times in the list here, I got them from this article, or estimated from that. That's all very rough estimates, so we do not claim that this is absolute correct values. And of course it can always vary, and it's not really a linear decay as we assumed here in the model. Normally it's quite fast that some decay starts early, and then other parts of the needles or for the other litter, that takes longer. So probably we should separate here, for example, the needles in like 2 fractions, one that decays quite fast, which is more the exposed material, and the more longer term fraction that takes longer, the more structural parts. Same for the leaves. The general structure can be solved quite quickly, but the structure in the leaf that is a little bit stronger, so that stays longer. So this is just a very rough assumption. We didn't look too much into it if we can really improve that very much, because we just took these extreme values and we saw that there's actually not too much change. Several percentage in between. but the model is relatively stable against these changes. So if we would change, for example, the decay time from needles down to 4 years or something, then it would barely have an effect on like the determination of the biospheric content. And I think for the general conclusion, and we're ignoring a lot of local effects that we don't know, especially from the 60s or so, we think that this is not the big influence.
Are there any other questions? If not, then I have one. Did you also, from what I understood, you basically just took into account that you could take up all CO2, but did you also take into account that you could have plant physiological things involved in the whole thing? So, meaning you could have like stored carbon. Did you consider that as an option?
Well, it was not in the model itself, but this is, I think, what we see in the, especially in the oak here, these very low values in the beginning that represent almost like the previous year or end of the previous year fraction, the same here. We think this is basically the old material that is used primarily in the beginning of the year. And I think this is also why the model basically doesn't really work and gives this very high value. The 1 point here hidden is 18,000%, which of course doesn't make any sense. And we don't see that really for the spruce and for the pine trees. There might be a little effect, as we see this, for example, here in 64, the first part is relatively flat. I would probably assume a little more raised there as well. But this seems to be a very small effect for evergreen trees. So that's why we initially did not.
I think we just, when we did a bit, we came actually up to similar results in our publication, and we rather explained basically everything by stored carbon. And you came to a little bit a different conclusion. Yeah, we will see what turns out to be right. Maybe it's a combination of both. Thank you.
Yeah.
So is this, there is one last question maybe?
Okay, I have a question. If your model is correct, then you should see the contribution of a different year have to be similar, right?
What do you mean different?
For example, like the bio content here, you can see one is about 20% for 62, and another one is 20%. But 64, you have almost 40 or 50%. And the same, if you have, the blue and the black.
The red one here is just like the extreme example with a very young litter. So this is not really realistic. So I think the blue ones here is what we deem the most realistic estimate. So we still get some variations that can be part of a wrong thing in the model, or maybe like non-structural carbon, as Lucas mentioned. But it also can be local things. So we don't exactly know how was any construction work, for example, nearby that might have affected the tree itself. So when the forest was cut, for example, there can also be like more windy seasons or something that would mix the atmosphere more. And also especially towards the beginning and the end, the growth seasons vary a little bit on temperature. So in Trondheim especially, everything is frozen until March basically, and so then only depending on the weather and the rainfall and so on, things grow and start growing. So they will also have some effect on this behavior of the curves here.
But another thing is, the environment, what you do is a rough estimate, right? But because at a different site, you have a different environment. And all the data here may be different for different sites. And then,
okay. So this is a very local thing, basically. So we always have to consider where the tree grow, if there can be an effect. If it's a very single tree on an island somewhere, then probably this effect will not be very large. There might be an ocean effect then. But if it's in a dense forest, maybe in a valley or so, then airflow will be quite limited. So.
Okay, I think with this last question, I would like to close this session, and we will continue after a coffee break. Thank you very much.
Just two information before we have the coffee break. Tomorrow morning we will move to Gallipoli by bus. So go to the registration desk and you will find some kind of form like this. Just decide and put your name.
So hello everybody. Welcome to the session about methods, machine and sample preparation. In this session the first speaker is Daniel Damaria from ETH Zurich, talking about high throughput AMS gas measurements. Please.
Thank you very much. Thank you very much for the introduction and welcome to my presentation. Today I will focus more on technical aspect because the application they have already their presentation in this conference. So let's start. Over the past decade, significant progresses were achieved in the AMS field thanks to the development of compact systems and hybrid ion sources that allow the analysis of samples in gaseous form. This led to an increasing demand and interest for radiocarbon gas measurement. And for example, this trend is clearly recognizable in the statistics of the measurement performed at LIP ETH Zurich. So that's why, to address the requirement of a higher sample throughput and level of automation, we decided to develop new methodologies and a new gas handling system, namely the double trap interface. Originally, the idea was to develop an instrument that was tailored to meet the specific requirement of biomedical companies performing so-called ADME studies, in which the fate of a C14 labeled pharmacological compound is investigated from its absorption into the organism until its excretion. The huge potential of C14 as a radiotracer for metabolism and pharmacokinetic studies was recognized since the invention of IMS back in the 70s, but only the introduction of hybrid ion sources that allow to perform gas measurement and so to skip the very demanding and time-consuming graphitization process made this technology more appealing for companies. Just briefly, the starting point of our technical development is the conventional setup used for IMS gas analysis at ETH. These slides give a brief overview of this system. The samples are first combusted using an elemental analyzer, which separates the released gases and provide a quantification of the carbon content. The gas interface gas is then used to collect the CO2 onto a isolate molecular sieve. The CO2 is subsequently released thermally into a syringe that has an adjustable volume to regulate the carbon flow into the ion source to keep stable measurement condition. And finally, the quantification of the isotopic ratio was performed using a Mikada's IMS system. And so, to improve the performance of this combustion-based IMS technique, we focused first on the combustion unit and the gas handling system. The double trap interface was designed for the couple with an elemental analyzer and an IMS system. The DTI addresses specifically the application that requires an increased sample throughput and also dealing with lower precision. And the aim initially was to achieve at least 200 analyses per day. The DTI introduces a revolutionary approach to the analytical process, since it features two traps, two zeolite traps that works in an alternating way. This allows to decouple the loading of the CO2 released by the sample combustion and the measurement phase, which run now in parallel for a quasi-continuous sample analysis. Additionally, the CO2 is now released at around 400 degrees directly into the ion source, skipping the use of the syringe, and so we can eliminate the very long and exhaustive cleaning routine of this piece. And in this slide, we see the timeline of the different processes running in parallel on the elemental analyzer and the two traps. The measurement time is set per default to 2 minutes because the targeted application involves generally the analysis of samples characterized by concentration above the natural abundance. So, even with 2 minutes, enough counting statistics can be obtained in this time. The overall analysis time for one sample is now reduced and is less than 5 minutes. And the combustion cycle of the elemental analyzer is reduced to 3 minutes and 20 seconds. But, of course, despite of the increased sample throughput, the quality of the result has to be still guaranteed. And so, reference standard and blank samples were analyzed throughout measurement campaigns to monitor the stability of the measurement condition and also to monitor the contamination of the instrumentation. OXA2 standards measured with the double trap interface were compared with the reference gas mixture of the GIS. And as you can see on the plot, no significant deviation were observed over the single studies, indicated pretty stable measuring condition. Important with respect to the blank level, it was important to show that a value below 0.02 fraction model could be achieved at the beginning of each measurement day. This is our target value, and this despite of the concentration that were measured on the previous day. And the fact that we can measure values that are even below 0.01 fraction model indicate that the AIDTI system is not limiting the sensitivity of this method, but the sensitivity is rather limited by the contamination that is introduced by samples that are a concentration above the natural abundance in the system. So, thus it is very important to reduce the contamination of the system to a minimum. This is particularly important for the biomedical studies that involve, for example, the analysis on samples, enriched C14 samples, that can have activities up to 1,000 times the natural abundance. Two types of contamination were identified. First, we have the crosstalk that indicates the contamination between consecutive samples and was quantified on set of 3 blank samples measured after an OXA2 sample. The crosstalk was reduced to below 1%, and this was achieved in particular by introducing a selection valve that let only the CO2 coming from the combustion of the elemental analyzer to transit through the trap. The memory of the system refers to the long-term contamination introduced in the instrumentation by the C14 enriched sample, and the recovery of the system was studied by observing the evolution of blank values at the end of a measurement day, during which spiked biomedical samples were analyzed. The presented example indicates that the crosstalk on the first blank is already below 1%, but however, even after 6 blanks, the target blank level of at least below 0.02 fraction model was not reached yet. And so the main source of this kind of contamination was identified in a suboptimal evacuation of the capillaries that delivers the cleaning and flushing gases, and which this part is located upstream the zeolite traps. And also the size of the measured blanks has a very big, huge impact on the recovery of the system too. And carbon content of around 200 micrograms have definitely this cleaning and recovery process of the system. Besides the new gas interface and the new measurement routine, we worked also on a more compact and easy to operate IMS system for this EA-DTI coupling. And the design of the LEA is the result of the research performed at ETH and ION Plus to investigate the low energy limit of IMS. The table gives a summary of the specification of the new instrument compared with the Mikadas. The terminal voltage at the acceleration stage is reduced to 5 kilovolt and for stripping energy around 100 kV. ALEA is now in operation at ETH since 2022, and Urs Ramsberger will present the performance of this instrument right in the next talk. So for question, wait for Urs. But yes, just briefly about the application. It was quickly recognized that the performance and the characteristic of the double trap interface could be adapted to several applications in the environmental studies. A first example is the ramped oxidation system ORO to investigate C14 variability in soils and sediment. But I won't spend too many words on it, since we had yesterday the very nice presentation of Marco Bolandini about this project. But just to stress a bit, the key point for this application is not, of course, the speed of the method, but rather the possibility to have a streamlined online system that allows a continuous collection of the products of the oxidation, followed directly by C14 measurement. So we don't have an intermediate storage of the CO2 collected from the oxidation. But let's move now from the earth to water. The accumulation of plastic litter in the environment has become a major concern of the actual society. The flow models indicate that millions of tons of plastic are entering the environment every year, and the trend predicted for the future is increasing. Therefore, several studies began to investigate under laboratory conditions whether nanoplastic accumulates or have an effect on marine organisms. But the question is how to reproduce realistic concentration expected for an aquatic environment. And seeking for an answer to this question, the Ramay Sid Sheikh contacted us, impressed by the sensitivity of the IMS technique. Her goal is to apply it to ecotoxicological issues by measuring C14 labeled nanoplastic air contaminants in general. In particular, the method to study the pharmaceutical in human tissues look very promising to be adapted to the detection of label and nanoplastic in aquatic organisms. And the aim of this collaborative project between LIP and the Ramay Sid Sheikh is to study the bioaccumulation at realistic concentration about 15 micrograms per liter. The project and the promising result of the preliminary test that we performed will be presented on Friday by Ramay Sid Sheikh. So be here even Friday morning to learn about this interesting project. But just briefly, the idea is, so in an uptake experiment, bivalves, for example MASPA, are exposed to label particles and collected at a regular time interval. After skipping the exposure, we assist to the depuration phase, during which the individuals are also regularly sampled over a period of 2 weeks. The sample individuals are then freeze-dried and mechanically grinded to get an homogeneous powder, and the samples are produced and interpreted and weighted in aluminum boats. And these were then analyzed at LIP using the EA-DTI method, like for the biomedical application. Many thanks for the students that prepared the grinded muscle. I think they could never have some muscle again after the production of these many samples. So, just to summarize, the DTI demonstrated over the past year an excellent and reliable performance for application requiring a high samples throughput and dealing with samples activities above the natural abundance. Its use was successfully extended from the initial niche of the biomedical field to soil and ecotoxicology studies. Moreover, Maya Sheikh was awarded Pioneer C13 grant for our project Imaging, and I personally look forward to start working together. Our task will be to adapt laser ablation coupling for AMS that was recently developed at LIP for semi-continuous otolite and stalagmite analysis to map and quantify C14 atoms inside organic tissues in general. So thank you very much for your attention.
Thank you very much for the nice talk. And are there any questions?
I was wondering how dangerous to run such active sample in a standard radiocarbon dating laboratory, both in terms of ion source and sample preparation. Do you really need separated laboratories or?
Yes, this is the best practice, to have really a lab that is dedicated for the radio labeling analysis, because maybe I can already anticipate a bit in the study that we performed, for example, but both on biomedical samples but also on the nanoplastic, we see already a background contamination that can be already above the natural abundance, that is maybe due to radio labeling experiment performed in other labs. And of course, it's better to keep separate these things and not to perform this in a lab dedicated to radiocarbon dating. But that's why it's very important at ETH that we have a dedicated system with a dedicated elemental analyzer for this application, and also that the double trap interface is mainly used for enriched sample, just to really keep separate.
You mentioned this project on nanoplastics. Yes. Does that include the huge field of microplastics as well? Because microplastics is being talked about enormously, and especially also in aerosols. So does that, or is it a different aspect of the plastic you are investigating?
Maybe, Maya, do you want to answer about this project later?
Yeah, so microplastic or nanoplastic, this is a definition about size. So the experiment we performed, I synthesized nanoplastic, so that was particle about 250 and 20 nanometers, because it's expected to be potentially the most hazardous form of plastic. But currently I'm also synthesizing micro sizes that we will be also investigating with the AMS. So the question is there, but all investigation about ecotoxicology show that when the size decreases, we will have potentially more impact about those particles. Yeah, because of the size and the transfer to membrane, the size do have a big effect. So nano sizes can translocate, and that's the first study I demonstrated that we have a translocation of nanoplastic.
And maybe if I can add something, that's why it's so important to have the IMS technique, because just thanks to the IMS technique, we have the sensitivity to detect this small nanoplastic by reproducing really this realistic concentration that we can expect on a natural environment. Because maybe using decay counting techniques, we will need too much nanoplastic to detect a signal, then will not be reproducing the environment. Oh, cantare, oh, nel blu, dipinto di blu, felice di stare lassù. No, o qua giù. Thank you.
know, our second talk is also from ETH Zurich, who's Ramsberger, talking about Lea system.
Good morning, everybody. I still think it's still morning, right? I think so. Okay. As announced before by Daniele, I will talk about the Lea system, which is a new system we developed for at low accelerator voltage. If we talk about Lea, we also have to talk about the Mikadas, which runs at 200 kilovolt accelerator voltage. And now the questions arise, how could we reduce this voltage, this accelerator voltage? And that goes back to a paper which came out in 2007 and was written by Schulze König. And this says that the using of helium as a stripper gas is, or the yield of the helium, or the breaking up the molecules is at much lower accelerator voltage. So this opened up the development towards this low energy AMS system. Okay, for all those who are not really familiar with how it works and which are working in an AMS facility like I do, here I briefly just want to explain how it works. So what you see here is the top view of our new system, the Lea, and at the lower end here, on the left side, is the sample changer, which contains a maximum of 44 targets. Then attached to it, we have the 40 kilovolt ion source, which where we produces the ion beam. Then the next one is the first mass filter at the low energy side, the low energy magnet. And then we have the acceleration unit, where this breaking up of the molecules happens, as well as the charge exchange process. After that, we have the helium, the high energy magnet, which is a second mass filter, and then the energy filter, the ESA, the electrostatic deflector. And finally, we have the C14 detector, which is a Bragg type gas ionization detector. The dimensions are 2 by 3 meters, which is the footprint of about 6 square meters. Okay, so we have tuned the machine that we have the ion beam path of C14 in detection. So this is here. It's the red trajectory. Okay. And at the same time, when we measure the C14, we also are able to measure the C12, because it gets a bit more deflected in the magnet because of its lighter mass. This is important that we can later on calculate the transmission. After that, we also have to, of course, detect this C13 and C12 on the high energy side. So we introduce a fast pulsing system which enables the injection of these isotopes into the accelerator. So What it means is that we just speed up the beam so that, for example, in this case, by 3 kilovolt, that C13 goes through the accelerator, and also then by additional 3 kilovolts, we can detect C12 on the high energy side. And here we see some typical values for our layer system. Maybe I mentioned this pulse offset, the pulsing system. It starts at -3 kilovolt, and this means we detect the C14, and then we give a small pulse up by +3 kilovolts, which is the plus B, in order to detect 313, and with an additional pulse, which is like 6.5 kilovolt, then we get the C12 into the accelerator. Okay, so what is similar and what is the difference between these two machines? Obviously, the low energy side is basically the same. We have the sample changer, same sample changer, the same ion source, the same box lenses. The fast pulsing system is also the same, as well as the low energy magnet. Then for difference is the accelerator. As we said, we had 200 kilovolt with the Mikadas, and with the LIA we only have 50 kilovolt, and that means we also need different high energy magnets as well as different ESAs also. And as well the C14 detector. Okay, this is basically the same detector, but it's run in a different operation mode. I will explain later. And yeah, finally the footprint. LIA has 6 square meters, the Mikada 7.5, so LIA has a bit smaller footprint, only by 1/2 square meters. Okay, and here we have a photo of that layer at the ETH site. You see on the right-hand side there is this gas interface, which just Daniele was talking about before. So that means the layer is also measuring gas samples, and this is running quite well. We have also the double trap interface there, and yeah. Okay. Back to the detector. So as I said, both systems have the same type of the detector, so Bragg type gas ionization detector. But since the energy is different, the ion beam, it's 420 keV at the Mikadas, and at the LIA only 140, we have to operate it in a different mode. So we have to change it from ion chamber region at the Mikadas to the proportion region at the LIA system. That means also that we have to increase the detector voltage up to 450 degrees, 450 voltage. Okay, so the gas we use the same, that's isobutane, and gas pressure, at the Mikada system we have around 20 millibars, the LIA system 9.5. What is important is the detector window. We used first a 50 nanometers membrane, so this is, the window is actually, it separates the isobutane gas from the vacuum, and the beam has to go through it. So since this energy is a bit lower, or much lower at the layer system, we had to get a smaller membrane, like down to 30 nanometers. What you can see here is at the energy spectra. On the left side we have the background events, and here in the middle we have the C14 events. And the red line was the measurement with the 50 nanometers window. And what we see here is that we have an overlap of the C14 events with the background events. So we couldn't really distinguish which are which. But this problem was solved by using a 30 nanometer membrane, and what you can see here, there is a clearly gap in between these two peaks. Okay, so the measurements which are done, we had first used the blanks and some standard measurements to test how good this performs, the layer system. So the blanks, both blanks are clearly under 50,000 years. What you see here at the blank 1 measurement, oh, the mouse is not. Okay, blank 1, so the first measurements, they're a bit higher, and this can be explained by surface contamination, because then it lowers, after several measurements, it lowers down to the level of 0015. And the second blank was also was a bit cleaner in that, or had less contamination, and it was already down to the level which it should be. So both blanks were older than 50,000 years. And with the oxas also we have very stable measurements. So the precision of the mean of each sample is around 1 per mil, whereas the mean of the means is even less than 1 per mil. So this is quite promising for further measurement. So we had to do the alternative test, how we can compare the Mikada system versus the Lea system. So what we did is we had to measure exactly the same samples. So we made 2 sample sets. They contain 7 standards, 4 blanks, 2 references, and 26 wood samples. The wood samples were consecutive annual rings of unknown age, which were determined by dendrochronology. The first set was from 2800 to 2825 BP, and the second from 2826 to 2851. So what we did is we introduced this first magazine, the sample set, into the Lea system and measured there. So we measured up to 1 million OXA2 counts, and these are the results here. And then we took those out and brought it over to the Mikada system, put it in there and measured, did the same measurement with exactly the same samples. And this is that result there. And also we had to do it vice versa. So we took the second sample, which was first measured at the Mikadas, and then brought into the Lea system, and there it was measured again with, and these are the results. So what we see here is we have an excellent agreement of the results. there is no obvious difference between the two systems in terms of the results and the precision. That means these two systems are exchangeable. They're both as good as the other one. Okay, so maybe for a little summary here, the specification. So what is different is the transmission. The Mikadas has only 48% of transmission, whereas the Lea has 56%. The blanks are in both systems very good. Oxas also similar. And precision, we were just seeing it. They are exchangeable. But what one big advantage has the Mikadas, and this is at the high energy side, we can measure with a high C12 current. It goes up to 40 microamps, whereas with the Lea system, we are somehow stuck at 25 microamps. So that means we can measure faster with the Mikada system by a factor of around 1.5, more or less. Okay? So everything is written in this paper here, and you find more results there. Okay, just a second.
Figaro, 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 Figaro.
Thank you for the nice song and the presentation. Any question or comments?
Yeah, when you changed your sample sets, the cesiated samples were exposed to air and may have taken up some carbon dioxide from the air, and you seem to see that because the second measurement, when you swap them around, was slightly higher.
Yes, that's a good point actually, and I didn't mention it, but we always usually omit, or in that case, we omitted the first run. So we cut that off because of these possible contaminations. So yes, so this wasn't taken.
Do you understand why you cannot apply the normal Mikadas current? Because the space charge is acting more mainly on the low energy side, and there you have the same energy.
Yes, I mean, we were also wondering why it doesn't work, and we don't have really an explanation for it. I don't know. One possibility was like space charge, but we are not sure what it is. Yeah.
Is the stripper tube the same in the Lea and the Mikadas, or was it adapted for the lower stripping energy, and that would probably also lead to larger straggling angles, so you need more acceptance, which also could, of course, limit the currents if it's not properly adjusted?
That's also a good question, and that, I don't know if these are the same tubes. That might, maybe Arno is here too, so he might know it.
The ion optical transmission, which means the number of atoms which going into the stripper tube and those who coming out of it, is in the Lea system 80%, whereas with the Mikada system it's about 95%. So this makes it much easier to adjust or to accept higher space charge from the beginning of the ion source, so the volume of the beam it can be accepted at a larger stage. So that's a point why it's maybe more difficult to run it at higher beam currents under stable operation conditions, but with limited maximum beam, they are absolutely equivalent in performance.
So it's exactly the same tube in it.
Of course, that's a very complicated process in order to calculate the energy loss and the straggling inside the tube and match it to the best performance you can do. So it's really matched to the conditions of 50 kilovolt acceleration energy.
Okay.
More questions or comments?
You don't really have to answer this question, but does the price of the facility scale with the energy?
So this one is the prototype, so you cannot buy it. It's too much. But otherwise, it's also, there is the Iron Plus. They made a commercial product out of it. They already sold, I think, 10 of these layers, as I heard. So it's already kind of successful, this product.
Okay, thank you very much.
Yes, thank you.
Okay, so today our third speaker is Bin Yang, talking about automated system for dissolved inorganic carbon analysis. Please.
Yeah. Okay. Buongiorno. Just before my main talk, a few words. It's a very special event for me. Thanks for organizer to provide this opportunity for me come back to Italy again. And 37 years ago, I was the first enter to Italy and complete my PhD and also spent all 10 years here. So Italy is a very special country for me and special people and beautiful sea and sun, so a lot. Thank you. Yeah, so I start my talk. And the topic is the development of an automated processing line for the extraction dissolved inorganic carbon from underground water, radiocarbon for radiocarbon analysis. Yeah, this work is done at Anston, and a part of this result was also present in the radiocarbon conference in 2022. So a few slides may be overlapped. So here is the overview. So I will give introduction, the DIC analyze at Anston and test of DIC line and the testing of the water trap and the CO2 trap and design of automated DIC line and the setup with the automated DIC line, testing of the line. And then there is some change of a CO2 trap and CO2 trapping efficiency against the DIC concentration and the process 10 samples, AMS result, and the summary. Okay, here is the manual DIC line currently operate at Anston. So there is, you can see from the left to right, the water vessel and the water trap and the CO2 trap and the pressure transducer. So this is a circulate water trap operated manually. There is a use of helium gas, and we use this line each day. We can make 2 samples, and there are 2 lines, so we can make up to 4 or 5 samples every day. And so it's because the high demands of this groundwater for either commercial and research, so we're granted to design a new automated DIC line. So here for make the automated line, and we first make a testing line. We use helium gas as a CO2 carrier gas at ambient pressure 1 bar, and when we mainly investigate the best temperature for trapping CO2 gas from the CO2 and the helium gas mixture, and the efficiency of the CO2 trap, and the capacity of the water trap. That's a bit challenging, and because we continuously will process 10 samples and without block by the ice accumulate in the water trap. And also helium flow rate for the processed water sample is also important. If you go too fast, there is no time to trap it, and also where too much water be carried to the water trap. So we designed the water trap. It's in the left side is a water trap. And as we found, the ice all accumulate in the import. You can see the photo, and from inner part of the trap, and this trap is merged in the liquid nitrogen and can be heated electrically, so the temperature ranges can be adjusted by from a minus 60 to minus 110. So it's good for trapping water, and we test it because the ice is trapping in the internal intertube, so we enlarge the outside tube and shrink the internal tube. That allow the ice trap there won't be blocked this water trap. And the CO2 trap has similar design. It's the one side of the aluminum bar was dipped into liquid nitrogen. The temperature of the CO2 trap can be controlled from minus 170 degree to minus 60 degree. So that is we use a low temperature to trap CO2 and use a higher temperature to release carbon dioxide. Okay, for CO2 trap, the efficiency for trapping carbon dioxide, we have tested it at the one CO2 trap at different temperatures. In the right side, this image diagram, you can see there is we made a few samples mix up between the CO2 gas and the helium gas. So the best trapping efficiency is performed at ranges about minus 170 degree to minus 160 degree for different gases. And so we decide use this temperature for trapping carbon dioxide. So based on the testing, we built this automated DIC line. From left side, there is a glove box. Inside the glove box, there are 2 rotation valves with 11 ports, so you can select 10 samples. In fact, that can be simplified, use only 1. And also the acid bottle placed inside, there is acid pump, can be pumping the acid into a loop. And there's a KNF pump, it's a water pump. That's 2 functions. One is you can pump the water and the molecule water into the reaction vessel through the water line. And also another function is during the CO2 extraction, they circulate the water in the water loop through the reaction vessel to improve the trapping efficiency. And during the trapping CO2, the helium gas will flow inside this reaction vessel and carry the CO2 gas, goes through the gas line. The gas line, first you have two water trap, and then I also put a sulfur trap that is used because real groundwater sometimes will have a presence of a sulfur, and that will kill the graphitization. So we need to remove sulfur. And that one is worked at 650 degrees with silver wires inside. And after that, there is a two water trap, and that can trap, two CO2 trap and trap CO2. And after collect sample, the CO2 trap and can release the CO2 and transfer the samples to one of the latest sample tubes that can be stored up to 10 samples in each 10 sample tubes. And the gas during the trap at end released through the CO2 analyzer, so we can see the check if the CO2 gas was completely collected or still have some residual CO2 pass through the analyzer. So here is the setup of this photo of this automated line. And from left bottom, you can see there is a big liquid nitrogen door. It's a 50 liter, and through that there is auto filling system go up, and this is from right to left. The first one you can see the reaction vessel, and then it's water trap, the CO2 trap, and then there is 10 sample tubes for the collect carbon dioxide sample, and at left end there is also the liquid nitrogen trap for cooling down the main vacuum tube, improve the vacuum. So there are two stages can rise up and down to put liquid nitrogen there for trap. So it's as I mentioned initially, we have tested the way the best temperature for trapping carbon dioxide. It was about minus 165 degrees, and we use that trap first for perform the automated CO2 sample processing. As we can see, immediately we found the problem. Initially, at the beginning, first sample, you get a higher efficiency, trapping efficiency. But later, gradually, the trapping efficiency dropped rapidly. So that is, as I think, is a reason is because this CO2 trap worked in the temperature range between the minus 165 to minus 60. At high temperature, highest temperature is minus 60. That is still too low for very low for very low. It's can trap water. The water, some water vapor pass through the water trap will be accumulate inside this CO2 trap, so that will consequently reduce the trapping efficiency for this CO2 trap. So for overcome this problem, I just switch back to a very simple design. It's just use a liquid nitrogen and go up and down. So the CO2 trap will dip in the liquid nitrogen for trap CO2. When then the door moves down, so this trap keep at 22 degrees at room temperature. So at this temperature, the water will be easily to be removed through the vacuum system. So the result is the red line that shows if we use liquid nitrogen directly, we get a very consistent trapping efficiency. So for the groundwater, what we're need to measure it, we get at Enstone, there are a very large variety of DIC concentration. It's, so for that, we need to check if this CO2 trap work good enough for all the range of the different water sample. So their concentration, we prepared some testing samples of between 0.05 milligram per 100 mil up to the 20 microgram C of 100 mil. And the result is clearly indicate. And also, I have used different pumping time. Different pumping time means in the up you can see it's a corresponding different sample water sample volume. So different volume for collect collect CO2. And that right side is a C mass we collect. The left side is a CO2 gas pressure. It's corresponding to the C mass. So there is a very good linear, you can see a very good linear relation. So that indicate this system and can trap carbon dioxide very good in all the range of different DIC concentration. So this is an example of two samples we prepared for trapping, and in the first, as you can see, this is you can see the pressure of the carbon dioxide we collected, and there are two numbers. It doesn't matter. You just see the left side number, and the first 5 samples slightly bigger than the later 5 samples, and I realized the reason is that because there are two rotation valves inside the glove box, the first pipeline for first 5 samples is shorter than the second 5 samples. So with the same power of pump, the second 5 samples is a flow rate is maybe 3% lower than the first 5 samples. So that means a smaller 3% smaller amount sample pumped into the reaction vessel. That causes a lower number. Finally, it's AMS result. And first, we made 3 blanks. The blanks is blank sample is made by put the calcium carbonate into the water loop, and as you can see, we have performed with a different C mass. There are some correlation. It's clear correlation. The large C mass get a lower PMC value, and then there are 4 samples compared with a manual line process. So it's all the 4 samples. We just choose there some with a very high PMC and some with a very low PMC, and interdigit with them. And as we see, the reproducibility of the result is good. However, still we can notice some small, minor cross-contamination memory effect. And also another small issue is the background is slightly higher than the manual line, so still some space to improve. So in conclusion, there's a automated DIC. The line can process 10 samples in 7.5 hours and consume about 50 liters of liquid nitrogen, unfortunately quite a lot. And it has consistent trapping efficiency for over 80% and in a wide range of DIC concentration. The AMS result indicates good reproducibility of PMC values, and minor cross-contamination hasn't been totally eliminated. For low PMC samples, value obtained from automated DIC is slightly higher than manual line. It's acknowledgement. Thanks for the financial support from New South Wales Government Research Attraction and Acceleration Program. Volare. Thank you.
Thank you very much for this nice detailed presentation. Questions or comments? We can start with Martin.
Yeah, I would like to ask about the temperatures that you had. You had this minus 170 degrees Celsius, but that was outside of the glass. And of course, glass is not a very good conductor for temperature. Do you have any measurements of inside where the sample is actually frozen?
Okay, the question is, of course, there's a glass CO2 trap, and the outside is an aluminum tube covered. The thermocouple is a contact to the aluminum, so I think the temperature should be quite accurate and even. Yeah, it's a very interesting result. Anyway, it's for the, as I observed, both for trapping water or CO2, you get too much lower temperature, doesn't work. And the best temperature is just a little bit lower than the temperature to be frozen at that point for both CO2 and water. Also, you can notice there is not trapped, all the things is not trapped at the liquid nitrogen or lowest temperature part, but always in the entrance of that part, that is the temperature change from room temperature to the liquid nitrogen or whatever temperature. That point, some point is temperature very close to the, I don't know, it's kind of harmonic, I think. I don't know how to explain, yeah.
At the beginning, you had a slide where you have shown the remaining carbon dioxide in the flux as function of the temperature.
Which?
Now, if you go there in this figure 3, why is the residual CO2 increasing if you go lower into temperature?
Yeah, it is true. What surprised me, but it is true. Yeah, the lowest temperature is I just directly dip the trap into liquid nitrogen, what I can do. And the other temperature is goes through the system or what I show in there. Yeah. Big surprise. Anyway, so the best for CO2, the best temperature for trapping is.
I don't understand this at all. And then I want just to make a remark. If we had samples with a very low DIC content, we did as first step put some air without CO2 through it for a few hours to get rid of the CO2 which is solved in the water. Because this solved in water mixes with the DIC after you added the acid.
Yeah, okay. Yeah, for the DIC, of course, we put acid to get the carbon dioxide emit. But this experiment, as I showed in figure 3, is nothing about water. What I did just through a bag, I put the helium gas, for example, helium gas inside and the carbon dioxide inside, and go directly through the first water trap and then CO2 trap. The result is shown here. So it's not about the DIC things. It's a direct result. Yeah.
Okay.
More questions or comments? Then I have one question. Did you ever try to reduce the helium flushing flow, the flow rate?
Yeah, I have tried to reduce the flushing flow, but there is a, once you reduce, there are trade-off. When you reduce it, there means the small amount gas will carry carbon dioxide go through. If you go too fast, there is not enough time to trap the CO2 gas. Anyway, the best way, it's not best line, I have to say, but I mean the best way is to make a loop. Maybe I will some time to modify it as a loop.
If you reduce it to zero, then CO2 will still freeze there. I believe so. Actually, in our system, it works like this. We don't use helium, and maybe the helium flushing is giving you the water, the huge water movement in the line. Okay, we can discuss it later.
All right, thank you. We can discuss
Okay,
it.
thank you very much. Thank you. So our fourth speaker is Konrad Judika from Poland, talking about micrograph line.
So, hello everyone. So my talk will be about Mewgraphy line, a high throughput, low maintenance, fully automated combustion and graphitization system. Before I start, just a few words about MewDose Solutions. So MewDose Solutions was established in 2018 when we released the MewDose system. The system is dedicated for luminescence dating, for measuring low levels of uranium, thorium, potassium, and for precise determination of environmental dose rate, which is crucial in luminescence dating. Last year, we started our sales in Germany. So where is the pointer? Oh. So we started our sales in Germany. Later we sold quite a few systems to United Kingdom, Sweden, Hungary, and a number of European countries. We also have some sales in China, Australia. Last year we've introduced the updated version of the MewDose system with active background reduction with machine learning algorithms. Currently, two systems are working, one in Australia and one in China. So you are not here to hear about the MewDose system. You are here to, so I'm here to present the Mewgraphy line. So the Mewgraphy line is a high throughput, low maintenance graphitization system. The system consists of 8 modules in standard configuration. Each module is entirely independent. This means that the combustion and the graphitization in each module is completely separated. So the entire process of combustion and graphitization takes approximately 3.5 hours. So during a workday, you can process 3 such batches, so it means that 24 samples can be measured, graphitized. So the system is modular, therefore one can start with a single module and later add additional modules, or those 4 modules in standard configurations can be extended. So in addition, the system is designed for dedicated add-ons such as step combustions, ramp pyrolysis, oxidation process, and there is variety of customizable temperature settings. So what is unique about the system is that it does not require liquid nitrogen, no any kind of working gases, and this includes helium, hydrogen, oxygen, and argon. So the first thing is that it is very easy to set up such graphitization laboratory, as a laboratory manager do not need to fulfill all the safety requirements and regulations. The other thing is that this equipment is very safe to operate. So if a safety is a concern, this is the system which can be considered. So the graphitization efficiency is about 95%. So 95% of CO2 is converted into nominal 1 milligram graphite targets. And a number of operational parameters of the system can be altered during the combustion and graphitization. So in this system, we are taking oxygen from copper oxide rods. This oxygen is used to burn the sample. Next, the gas is transferred to the graphitization unit. And in the graphitization unit, we use zinc. So the end product is graphite. The entire process is fully automated. So after loading the sample, there is not much work to do by the operator. So after loading this, so this is the screenshot of the software. After loading the samples, the system automatically checks whether there are any leakages. It preconditions itself. Next, the sample is burned. So this is a rather unique feature because here you can, for example, the red line shows the pressure during the combustion. So after the combustion, the gas is transferred to the graphitization unit. So we've processed a number of samples. Here are very well-known samples: the oxalic acid, phthalic anhydride, background, and a number of materials from the International Atomic Energy Agency. So what is interesting here that the red line shows the temperature, the blue line shows the pressure during the combustion. So one can see that, for example, the oxalic burns really fast, while other reference materials such as C3, C4, C5, which is cellulose and wood, respectively, require much higher temperature. So those heating rates were adjusted for the speed of combustion. So it means that we are heating the quartz vials as fast as possible without breaking the glass. The system automatically detects whether the sample is completely combusted. So, for example, the peak combustion temperature in the oxalic is 800 degrees, while the lower reference material, C4, requires longer combustion. So yesterday we saw a few thermograms, and this is a kind of form of this thermogram in an integrated form. So it means that even the module which we brought here for demonstration, in this module we can extract certain parts of the carbon dioxide, which was extracted in certain temperature. So we can throw away the unwanted carbon dioxide, or we can process graphitizations from variety of temperatures. Next, the gas is transferred to the graphitization sector. So here are some graphitizations. They correspond to the combustions that were shown on the previous slide. And as you can see, the system needs about 100 minutes for the complete graphitization. So some lines are a bit shorter because the system automatically detects whether the pressure stops to decrease. And therefore, some graphitization processes take somewhat less than 3.5 hours. So on the left side, we have a batch which we sent to the University of Georgia, the last batch which we sent there. So the agreement between measured and expected values is pretty good. On the right side, you can see measurements which we've made in Silesian University of Technology, on Mikada system. Again, all of those points lie on a straight line. The numerical values also show good agreement, so one could say that those points are pretty large. Nevertheless, when we would look closer at those numerical values, there is also a statistical good agreement between mu graphi line and the reference values. So what about cross-contamination? So the system was designed to practically eliminate cross-contamination. So the first two samples are rather rich in carbon-14, while remaining 3 samples have a low C14 concentration, and there is no kind of memory effect visible in our system. Regarding the size of the samples which can be graphitized on our system, so routinely we work with 1 milligram carbon samples. Nevertheless, we also process samples as small as 35 micrograms, and they were also measured with Mikada system. Nevertheless, the smaller the sample, the worse counting statistics, and there is a balance between the quality of the results and the size of the sample. So we have 3 posters which describe the things which can be done with the mu graphene line. So Kasper on the left is presenting a variety of sample types which can be processed with our system. And we can process small samples, samples with raw carbon content, carbonates. Max has a poster about carbon fractionation in our system, and we've measured this on the IRMS and on Mikada system. We didn't detect any kind of fractionation in our line, so this is a spoiler of Max's poster. And finally, Fatima has a poster where she used the mu graphene line to extract carbon from iron. So this technique can be used for dating iron artifacts. And this entire process takes roughly a few hours instead of manual operation of extracting the carbon from iron, which takes days. So the summary. So routinely, the system is offered with 8 independent modules. There is no liquid nitrogen nor any kind of working gas required. The combustion is very advanced, so we can set up the heating rates, the end temperatures. Routinely, we combust the sample in 1000 Celsius degrees. When the quartz vials are good, we can increase this temperature up to 1100 degrees. So the water is removed with the Peltier cooler trap. We use silver to remove sulfur. And basically the entire process is fully automated. So before the system starts, there is a leakage test. If sample is too large, there is overpressure detection, and system automatically adjusts for the size of the sample. The entire process is fully automatic without any bugs, and this ensures consistent results and very reproducible graphitizations. The entire software is pre-installed on a PC. The software is very user-friendly and intuitive. And it's time to sing the song. Volare, oh. Thank you.
Thank you for the nice talk. Any comments or questions?
Thank you for this presentation. So nice black boxes. And I just don't understand how you move CO2 from one volume to another if you don't use liquid nitrogen and carrier gases.
Yeah, so there are a number of patent applications, patents in the system, and there are things which are not revealed. This is a commercial product, so this would be the answer, which is, I know that it's not satisfying.
Thank you.
Hi. Yeah, maybe this is also patent protected, but where does the oxygen go to? If I see it, you reduce CO2 to CO using zinc, and then CO to C using iron. If they're not mere catalysts, so they they get oxidized, and do you then have to replenish them, or how does that work?
Do you talk about the combustion
or
the graphitization?
The graphitization.
So in the graphitization, the oxygen is attached to zinc.
Okay, so you have to replenish the
yeah.
The
So the zinc is the reagent which you need to supply to the system.
And the iron is a catalyst, or does it also get oxidized?
Yeah, the iron is the catalyst. Yeah.
Okay.
Have you ever tried with higher activities, like 1000% modern or something like that?
No, we didn't try with higher radioactivities.
Will you plan to? Or do you
Yeah,
plan
well,
to?
we kind of work in a laboratory where we date objects. And, well, I was told that it's not good practice to experiment with higher radioactivities.
But if you are interested in doing environmental studies like around nuclear power plants, for instance, then you can encounter higher activities.
Yeah, yeah,
so
I'm
if you
aware of
want
this.
to have that market, I think it's a good
Yeah,
idea
I'm
to
aware
try.
of this, but there is... so we have this kind of limits what we can do. And in addition, we don't really have access to higher radioactivities.
You can go out in the environment of a nuclear power plant and you will find it.
Yeah.
I can give you some samples.
Yes, but I will not be able to process this in my laboratory. So I will be allowed.
More questions?
Regarding the filaments graphite that you produce, is important for us that they be homogeneous in relation to the beam current. Have you evaluated that?
The homogeneity of
The filaments graphite, the graphite that you produce, have you evaluated how homogeneous and the relationship of the beam current that's produced at the spectrometer?
The graphite is, we have a quite good reproducibility, and the current is usually very, larger than you would expect from other systems.
If I understood you right, you're using only zinc for the graphitization, not titanium hydride? Or
Yes,
something?
only zinc. Only zinc.
Okay.
Do you plan to adapt this model to gases sample also?
To gas samples?
Yes.
So we were extracting some, because this tools offers a great opportunity for someone who would like to, for example, convert the gas to graphite. And it can, in principle, it can be done, but at the moment it is not built into the system.
If there are any more questions, I have also one. Did you try carbonate? Carbonate? C1
Yes, we
or
have. So
C2?
Casper has a poster with carbonates. So we talk about this at AGU. So we've processed 2 carbonates from the International Atomic Energy Agency.
Okay. And another short question. You mentioned you are able to produce graphite from 35 microgram of carbon.
Yes. So
That was
this
the
is
lowest.
we deduce this from the pressure.
Okay. So do your system adjust the amount of iron? Is it auto-adjusting?
No, we didn't
Or you
adjust the
keep
amount
it?
of iron.
You keep?
Yeah, we kept it constant, but so those are just some kind of, those are just preliminarities. So I know that there are many things which can be done with the system, but
And my question was that, is your system able to adapt according to the amount of carbon, the amount of iron, or it is fixed?
Yeah, so the iron is, there are, I believe it's something like 5 milligrams of iron, and we always put the same amount of iron.
You add previously, so you don't change it after the measurement of the pressure. Online, you don't change the iron.
Yeah, so when the system is prepared, we need to stick to the system 3 vials, one with zinc, one with iron, and one with sample copper oxide and silver. And this vial with iron needs to be replaced and manually loaded. So one can in principle, put different amounts of iron in there for smaller samples.
We have a little bit of time still.
Okay, I had a question. Yesterday I saw you use a lot of copper oxide.
Yes.
I just wonder, you can reduce the background by reducing oxide or not?
So the question is whether we can reduce the background or...
Yeah.
Yeah.
Yeah, the contamination.
Yeah, the contamination from the copper oxide.
Yep.
Yeah. So at the moment we've tried to heat the copper oxide and remove the remove the carbon, so we can do on this line. Nevertheless, there are other. We are currently at the limit of the Mikada's detection capabilities. So to test this, whether we can further reduce the background, we would need to have access to different types of machines.
Okay. And is the lowest carbon mass you can run in your system is 35 microgram, or is it right?
Yeah, it should be somewhat larger.
Okay.
Somewhat larger. Yeah.
If no more questions, then thank you very much.
Thank you.
For presentation. And thank you for coming to this session today. This was the last talk in this session, and I thank you.
Thank you, Michi. I have a few announcements. First of all, do not remember that we will take a photo here, right now. So before going for lunch, just try to join me here and we will take the first picture. Then second, do not forget to sign for the buses for tomorrow. There are two sheets on the registration desk. You should sign either bus A or bus B. And third announcement, this evening we will have the guided city tour. So if you want to join it, you have to sign on another sheet which is always at the registration desk. So a few signatures we are asking.
So come here.
Margielewski from Krakow, and he will speak. Oh, there is a huge list of co-authors. He will speak about wood and Polish peatlands. Please. Okay.
I have to repeat. Ladies and gentlemen, my name is Wodek Margielewski from Krakow, from Poland. On behalf of many authors, 19, how is visible in the first slide, I would like to present you a problem connected with paleohydrological changes of Polish peatlands during the Holocene, inferred from subfossil pine, Pinus sylvestris, and oak quercus, dendrochronology, and peat multiproxy analysis. Within the European peatlands, fossil woods, fossil stems are very popular, and pines or oaks tree trunks are extracted during the exploitation. Up till now, dendrochronological analysis of these species have been carried out in Germany, Holland, England, and Ireland, Finland, Sweden, Lithuania, and Alpine region. On the basis of our research, we supplemented these records on Polish territory, where we elaborated 10 peatlands rich in tree trunks, fossils, of course, and buried in the peat of pines and rarely of oaks. Bog pine and bog oaks, it's not special species, but this Pinus sylvestris and Quercus robur. During our work, a total of over 2,400 tree samples were taken for analysis. At first, methods. Classical methods connected with standard dendrochronological methodology was used. Normal measurements of the tree ring with Eklund microscope and measurements of 14C concentration in various laboratories. The age of relatively dated samples was determined with the wiggle matching method with a use of Oxcal program. This method is necessary for us for construction of floating chronologies. Pitlat sediment cores were collected with the Instorf sampler, a Russian sampler, and samples for multi-proxy analysis of pit sediments were taken from the cores at interval 2.5 and 5 centimeter. For sediments, the following analyses were performed: loss on ignition, palynological and non-pollen polynomorphs analysis, macrofossil, Cladocera, diatoms, Chironomidae, and geochemical. One of our reviewers of our paper said us that this a list of shopping. Maybe yes, maybe not, but this complex of methods are very valuable for reconstruction of environmental changes during the Holocene. First site is located in south part of the Poland in Orawanowy Targ Basin between Tatra Mountains over the 2,005 meters below above sea level and Gorce Mountains. Puścizna Wielka Raised Bog. Puścizna Wielka is a great empty land. Is located at, how I said it, Orawanowy Targ Basin. And during pit exploitation, industrially, numerous subfossil pine, only pine trunks were excavated. 750 samples were used for dendrochronological analysis. Over there is Professor Marek Krąpiec, organizer the Radiocarbon conference in next year in Krakow. Okay, on the basis of wiggle matching and dendrochronological analysis, Professor Krąpiec elaborated 5 floating chronologies of pine. Floating, that means the limits of each chronology is no accuracy, is probably. What is the interesting in these chronologies? Very abrupt encroachment, the trees on peatland, and very short time of dying of phases of these trees. What was a reason of this situation? I will show you for a moment. There are a period covered by floating chronologies. And floating dying of phases, phase of death, mass death of trees, pine trees in this case, in peatland, are presented on the age depth model. We try to correlate of our floating chronologies with absolute chronology of Kurt Nicolucci, Willy Teigl, and Uwe Heusner from Germany, from Alpian region, without any success. Because the correlation of our chronologies with absolute chronologies was impossible due to that Orawanowy Targ Basin is Polish called pool, and specific climate is very important reason for this correlation, or rather not correlation. Three sediments profiles were collected with Instorf sampler for analysis from Puścizna Wielka. The bottom part is formed by minerogenic pit, upper part with ombrogenic. The beginning of the paludification of reservoir was in 5,288 years. Over there is position of floating chronologies in the profile and very picturesque artifact Neolithic man we found during our research. And the paleobiological analysis, pollen and non-pollen polynomorphs of the sediment profile of the Puścizna Wielka peatlands indicate that phases of mass dying of trees, dying of phases in the peatland were related to the elevation of groundwater level during extreme climate humidity growth in the Holocene. When the peatland was drying, their surface was colonized by trees. When during the climate humidity growth in the Holocene, the table water was rising, all trees were dying. It's a simple secret of floating chronologies. We change our place, we go to northern part of Poland, Rucianka peatland, northern Poland, exploited using industrial methods, using milling, numerous trunks of subfossil pines were excavated during pit exploitation. About 700 of them were used for dendrochronological analysis. In addition, also some stems, so fossil stems of oaks were elaborated dendrochronologically. And two oldest floating chronologies, bog oak and bog pine. This is only one floating chronology. This is one of the oldest pine bog chronology. Dendrochronological analysis showed that oaks grow in the sedimentary basin before the paludification and formation of the peatland. We are still have only floating chronology of oak. Hocus pocus, and we have absolute chronology. We, in effect of teleconnection, correlate our floating chronology with absolute chronology of Uwe Heusner from North German absolute chronology, and look the difference between floating chronology and absolute chronology beginning. 15 years, less than 1%. And our floating chronology, of course, in this case, are very precisely. And profile of the Rucianka peatland. And for floating chronologies in the profile scale, all of the floating chronologies are connected with the pre-paludification stage of the peatlands. Only one is connected with the first stage of the ombrogenic peat formation. The oldest dating from these sites in about 2,760 years, Cal BP. At the beginning of very wet subatlantic phase, these peatlands were formed. And how I said, 4 floating chronologies of the Rucianka bog pines. For a moment, I will show you the way for the change it for absolute chronology. And Rucianka pollen and non-pollen polynomorphs analysis versus floating chronologies. The presence of Archerella flavum, testate, amoeba connected with high water level, finished all living of all trees. The same is connected with the Cladocera, when bottom dweller species signet finish of pine bog trees. The same is connected with the macrofossils analysis and Chironomide, but in the case of Chironomide, the fluctuation of water level is more different than in another. Budwity peatland, also northern Poland, intermoraine depression during peat exploitation, using the industrial method. Numerous subfossil pine trunks have been excavated. This is a very picturesque shape of rest of these stumps. 500 samples were used for dendrochronological analysis, and some oaks stems were used for dendrochronological analysis. Also, what is the interesting? Exploitation field, coring out of the exploitation field, and place of dead forest. 1.5 meters below the contemporary ground level, we found dead forest. Rest of stems still rooted in ground. Also, bog oak were found, and on the basis of wiggly matching and dendrochronological analysis, we elaborated 4 floating chronologies, various age, and the oldest was 5,882 years, the youngest to about 2,000 years. What is interesting? Red asterisk shows the samples taken from a dead forest. For one surface covered by stems still rooted in ground. What is the problem? Problem is connected with them that 2 chronologies are differ 1,500 years. Why this situation is possible, I will show you for a moment, and 2 picturesque floating chronology of oaks. And profile of Budwity peatland, the beginning of the peat accumulation, firstly minerogenic, then ombrogenic, was connected with the Atlantic phase, and time range of the chronology means stage of peatland settlement are signed as green for pines and brown for oaks. What is connected with the strong difference of age of 2 floating chronologies? I remind 1,500 years in one flat level. It is connected with very low sedimentation rate or hiatus in sediments, don't indicated yet by pollen analysis. Very interesting problem. And position of floating chronologies on the results of geochemical analysis. This is indicator of high water level, relation ferrum to manganium. Large peaks show large water level. And isotopic carbon curve showing the growth of the temperature. And traditional floating chronologies on the background of pollen and non-pollen polynomers analysis. Archarella flavum, typical for high water level, finished life of trees covered the peatland. The same is connected with macro remnants of plants, very picturesque trapanatans, water nuts, very interesting plant. And the same connected with the Cladocera, blue color is cyanide species connected with the open water, the same with diatoms, and Diptera and Chironomidae also. And correlation of mass germination phase and mass dying of trees phases with paleoecological indicators shows that encroachment of trees on peatland was connected with drying of climate, drying of peatland, and dying of phases. Death of trees was connected with the increase of water table, connected with the growth of the climate humidity during the Holocene. We have 3 minutes? Yeah. And next example, Imshar peatland, northern Poland, 3 pine floating chronologies and position of chronologies in peat profile. The beginning of this paludification was connected with younger dryas, late glacial. There is very interesting problem connected with the hiatus. In deposit hiatus is connected with strong drying of peatland and colonization. This part of peatlands at that time seems to be logical because surface of peatland was quite dry. Oh, nice. And finally, correlation of our results of our research, floating chronologies, and one absolute chronology of bog oak Rucianka peatland shows that the oldest floating chronology in Polish territory is connected with the boreal. This is Podemszczyzna over there. And the younger also, but it concerned the oak. And the finish of the growth of trees on peatland was connected with water table rising in the peatland. And expected long time conclusions. Over 2,400 samples of tree trunks buried in the deposits of 10 peatlands in various parts of the Polish territory were analyzed. Some of peatlands existed since the late glacial, some from the subatlantic phase. Over there are the time range of floating chronologies elaborated by us. The developed chronologies of the bog pine make it possible to reconstruct paleohydrological changes within individual peatlands. Recorded in the form of trees germination and dying of phases which are correlated with the phases of climate drying in first case and climate humidity growth in the late glacial and the Holocene. Absolute dating of elaborated floating chronologies is planned based on teleconnection with absolute pine chronologies from northern Germany and Lithuania, as well as based on the identification of the Miyake effect recorded in tree rings. Particularly interesting is Miyake effect 660 BC, because on the basis of this research in Józefowo peatland was elaborated absolute chronology 835, 544. Józefowo peatland is in the neighbor of the Podwity and Rucianka peatland. And finally, to the teleconnection with the absolute chronologies of the oaks of northern Germany, of Dr. Uwe Heusner chronology, it was possible to develop an absolute chronology of the oak from the Rucianka site. It covers the period 1656, 1169 BC. This is the first oak chronology in the Polish territory. And thank you very much for the attention.
No singing. Okay, we have time for very short question. I was a bit generous with time. Questions? It was a beautiful overview of so many
And
sides,
singing.
very beautiful.
In the end, yeah. No? Va pensiero sulla lidorata. Thank you very much.
Okay, we have now time for next Polish name. Natalia will speak. Natalia Piotrowska, High Resolution C14 and OSL chronology for the Aeolian soil succession in Łaskarzew site in Poland.
Łaskarzew, yes, that's one of the many names that I will display, but I hope you will remember at least this one. So I work for the past several years in a team of scientists on the chronological frame for the land dune deposits in Poland. There are people from our lab doing the radiocarbon dating, OSL dating, dose rate measurements, but we also, of course, need field work people, so we work with geographers, geomorphologists, pedologists, and so on. The main reason is that we have a lot of very beautiful inland dune areas and also less sites in Poland because Polish territory is covered to much extent by so-called European sand belt. So these aeolian deposits are the remnants of the last glacial environment, and of course they do record the climatic changes, and the rate and the kind of deposition is related to the climatic conditions. So we want to explore those sites. At the beginning, I'm going to show you this state of the knowledge before we started extensive studying. So the state was based on the papers from the 80s and 90s of the late 20th century, which was there are two soil levels in the aeolian deposits, one corresponding to Bolling and the second one corresponding to the Allerod warming phases of the climate. So only two levels, and in between we have usually some sand layer and of course no nice vegetation cover during the younger and older and oldest dryas. But what we found in the profiles as a team, we found that there is multiple levels of soils, at least 3 layers corresponding to this time period, found in superposition many sites with much more than 3 layers, and also multiple post-fire layers composed of quite a lot of charcoal grains. As an example, I'm showing a few photos here. I hope you can distinguish. Maybe it's not that straightforward for everybody, but at least for some of the sites, maybe if we zoom in, yeah, you can clearly see 3 dark or even maybe more dark layers within the sand. So the sand is as you would like to have in your sandbox. And in Ostrołęka and in Dobroń side, you clearly can distinguish much more layers corresponding to some vegetation development on a dune, on the sand. So these are the examples, and we were, of course, wondering why and how this record was, how these sediments were formed. So the hypothesis is that these are the late glacial, short-term climate oscillation recorded there. So I asked ChatGPT to make this slide more attractive. You can have a look and some fun. And so these oscillations, of course, are recorded in ice cores. They are also as well documented in terrestrial archives. We have lake, pit, and so on, sediments. What we also record are the fires, and the fires are not only are also recorded, but they are also modulating the dune formation. So for dune formations, also the fires are quite important phenomena. So the question is, can we see those in our records? So 2 years ago, a paper came out in Radiocarbon when we summarized the data from the literature, and some part of the data we have already acquired. So there are around 100 radiocarbon dates. As you see on the summed probability, this is the dark plot, and the dates are here. They are distributed through the, let's say, late glacial time. Only 2 dates with the age for the pleniglacial, and still we can see in the density of these dates some peaks which might correspond to this short-term climate oscillations in Poland, recorded in ice cores and then also seen in Poland. But that's not too many dates. Some of the dates are of, let's say, 80s, 70s from gas proportional counters. They have large arsentaities, which results in, like, for example, for those sites, although we have scrutinized them, and that's the picture we got, but we, of course, want more. So there's a project ongoing or just about to finish with such a long title, as you see. So 51 sites were selected for these multi-proxy investigations. It's quite important that we keep the methodology quite consistent for those sites, how to recognize those dark layers, how to describe them, how to identify them, and then how to date them using radiocarbon and OSL dating. I will not make you read those names, like Toruń, Katarzynka, or Ostrowy Tuszowskie, but Łaskarzew is the site. I'm going to show you the results. That's quite an exceptional site. It's a parabolic dune close to the river Vistula, and in the southern part of this dune, people start to exploit sand. So it was quite easy to get there, and it facilitated the field work to recover the samples, because for OSL, for this kind of, there are meters of the sediments they need to be exposed to collect samples for OSL. You see those holes here, and some also dark layers interact, and some sand, yellow sand and dark organic layers. Here is an example of the very distinct dark layers, and from the first glance you already expect to have nice charcoal from those layers. So in total, in Łaskarzew site, 13 organic soil or charcoal layers were identified. That's quite an exceptional number of soil levels. We usually have at least, let's say, 3, but 5, 6, sometimes a bit more, but this site is exceptional in richness of those layers. We have chosen the samples for radiocarbon dating, doubling the number of charcoal grains from each layer, and 18 samples for OSL. So for the radiocarbon, we used standard methodology, like picked the grains. Of course, our technician Cinderella's picked those grains under the microscope. Then we applied the acid-base acid treatment, graphitize in H system, and then the graphite was analyzed using our Mikada's spectrometer. For the OSL dating, some people may not be quite familiar with, so don't be fooled by this simple equation. It looks simple, like the H in a dosimetric way is determined by the so-called equivalent dose. So this is the dose of the radiation absorbed by the quartz grains, which act as a natural dosimeter in this sense. And if you know the dose rate, which is the dose rate per year, then if you divide those two values, you should get an age of the sediments. So the equivalent dose is measured in the luminescence readers as a luminescence signal, and this procedure requires also prior preparation, like sieving and using chemicals to remove organics, to remove carbonates, and to remove the outer part of the quartz grains also by etching with HF. And then my colleagues applied the single aliquot regenerative dose protocol to measure the total dose absorbed by the quartz grains. And we also used the Canberra gamma ray spectrometers for determining the dose rate in our samples. So I'm not going to read all the numbers, no worries. That's the example of some profiles just to show you that we really do the job with a high resolution. These are exceptionally well dated sites. So black numbers correspond to OSL ages, and the blue show the radiocarbon ages. Of course, we date the material that we have in case of those sites, so sometimes we have more samples from OSL, sometimes we have a bit more from radiocarbon, and in general those ages correspond well. So here's another chart illustration about agreement of the two methods. That's what he gave me. So that's one of the examples. You see that the ages, they do correspond. There might be, some slight shifts also which can be explained by the nature of the dated item that we have. But in general, they do agree quite well between those two methods. So we were really happy to get those. And the dates we get for Łaskarzew site, 26 dates, from 2 from each charcoal layer. We sometimes observe there is no homogeneous ages within the layer first and the second, and also we have one outlier which looks like redeposited grain from the deeper layers here, but usually within the layer the ages are quite consistent. So when you summarize them, you see the ages of those layers. These are the single radiocarbon ages. More of them are located between, let's say, 12 and 11.5 thousand years BP. Then there is a gap of 1,000 years or even 2,000 years with no deposition of charcoal in Łaskarzew, and then we have another group of the dates. So that's what when we summarize them, and when we summarize them also here smoothed curve, and on the plot with the short-term climate oscillation, we see that the general picture is similar to the one that we have already published, and we don't have the charcoal and or soil or vegetation corresponding to, let's say, younger Allerod and younger Dryas period. So this is quite consistent with another sites that we have in our project we have investigated. So during the younger Dryas, some of them do have soil layers, but not of them. Sometimes there's only aeolian deposition. So that's why we think, and even OSL people didn't protest, that the radiocarbon ages are reliable and they do show the real ages of those sediments. While when you compare with OSL dating, you see that we have a huge difference between those two chronologies. These differences reaching thousands of years. It's not a single shift like in the previous study. Even if you have those small shifts in or inhomogeneity in radiocarbon ages, still these are not explaining the difference between C14 and OSL. So of course my colleagues checked the grains for the proper qualities like sensitivity. They checked other protocols for OSL measurements, but basically if you notice on the photo, these are really nice quartz grains, and they also, in the sense of measurement qualities, they behave very well. So what we suspect at the moment is then the second part of the equation of the for the OSL age, which is the annual dose rate. So here are the few examples of the concentration of uranium, thorium, and potassium, which are the main components of these dose rates. So for Łaskażew, the uranium is a little bit, let's say, depleted comparing to some other sites that we see only examples here. With thorium, it's quite similar. This site is exceptional. But with potassium, we see that the Łaskażew looks quite depleted in the potassium. And when you see also the, let's say, average dose rates for these example sites, you see that Łaskażew has a quite exceptional and low dose rate measured by gamma spectrometry. My colleagues also investigated some corrections, but none of them so far gave a correct answer how to reach closer to you can get closer to the radiocarbon chronology, but not as close as we would like to see. So we plan to, of course, investigate this case further. I will not maybe answer this question why. We have some ideas, but what I want to highlight here, maybe that we do see this more changes, more variability in our sites, and not always this large number of analyses we need gives a good answer. We need cross-checking with the methods. If you want to find a nice map with climate chart during the Allerod Stadel, that's what ChatGPT says. These are my colleagues in a sandbox, and one girl, PhD students, but you know, the big boys and big girls in the sandbox. And I need also to acknowledge my sponsors of this study and of my stay here, National Science Center and the EU supporting project. Okay, thank you. Should I sing?
Śpiewasz?
Śpiewam? Volare, oh, cantare, oh,
you, Natalia, for this. Oh, it's so loud. For this very interesting comparison. We have already Slava jumping up, and then Suzanne. Perfect timing.
I have two quick questions. First, as I understand, the C14 dates you showed in the beginning, they belong to the colder episodes like Younger Dryas and the warmer ones like Berlin Kaleriot. So, and can you say, maybe repeat, maybe I missed it. So, to which climatic episodes the formation of dunes is mostly associated? Cold ones or warmer ones? Or it's both?
I would say it's both. It's depending on the site also. So in some sites you have clearly only sand formation during the Younger Dryas, which seems quite logical. It was dry, it was cold, so no vegetation. But in some sites we have found a small layers of organic material from this period also. So I think this should be plotted also on some kind of geographical map. I don't know how to do it, but that's the idea. Yeah. And in general, those warming episodes are richer in organic levels.
You showed some numbers of gamma spectrometry measurements. Were then the units becquerels per kilogram of dry weight? It was one of the last slides.
This
that
one? Huh. Oh. I didn't ask my colleagues about the units. Sorry, that's.
You can let me know.
I think it's per kilogram, but Konrad is more familiar. He can. Yeah. Grace per kilogram or per year? Per kilo year. Yeah.
So in the table there are radioactivities in becquerels per kilogram, and on the right table there is dose rate in grays per kilo year, per 1,000 years.
Okay, yeah, thank you.
We have one more question here in front from Suzanne. I guess on OSL. She's the expert also here in the room.
Yes, thank you. I'm very fond of these comparisons, but I feel a bit sorry for your OSL colleagues because the only real method to date a sediment layer is OSL and not radiocarbon. It is wonderful if the radiocarbon age coincides with the OSL age because that's a tree that grew and it's not growing from the sediment, and it's not doesn't have to be contemporaneous to the sediment accumulation. So I noticed that you think the OSL ages might be wrong, but the radiocarbon charcoal should be the right one to build your chronology on, and I would like to know why. There was no doubt about old wood effect or bioturbation. I think on OSL the largest error you can do is the water content, which determines your dose rate. And I don't have any doubt about the 0.5 in dose rate because the more sand you have, the less radioactivity you have. When you go to Namibia, when you cross the desert with a cigarette, you increase the radioactivity by 200%, but when you go to Troy in Turkey, where you have a granite underground, then you have a dose rate that nearly explodes. So I don't think the 0.5 is not reliable.
Mm-hmm. Yeah, that's the water content we also looked into, and from the first glance, let's say, my colleagues told me that it can shift the OSL definitely, but not to the extent to match them. Of course, it's a problem of these water content measurements in sand. You don't know the water content 3 or 4 or 10,000 years ago. Of course, that might be a problem. So what we also want to check, if the potassium, if there is a possibility that it's a bit mobile, and if so, we would like to check also the lowermost layers if we see any traces of increased accumulation of potassium in there. There was one side with this. So regarding the radiocarbon, because at the present they show this consistent picture, and also these were pure charcoal, and we omitted any roots like which could, you know, renovate or give younger ages. That's what we think that it's the right way. Okay.
Thank you. I think there is another coffee break for big discussions, and we have to move to the next presentation. Thank you, Natalia. And we have Alexander Cherkinsky. He will keep on time, speak about comparative C14 analysis of different materials in lake sediments. I will say 5 minutes.
On this slide, you can see our 500,000 volt piletron accelerator, which is actually only 5 years young, but it's still running, and it's working about 80–85% per year. And actually, this machine was used for all radiocarbon analysis here. Okay. And our aim was defined which material is actually more reliable for dating of lake sediments. And we use a simple model by Cohen, which is actually very similar to the soil formative process. He defined the forces which can create a lake he called it archive, okay? And that's a climate, watershed geology, watershed regional vegetation, regional aquatic biota, and human activity. And these forces create sediments accumulation, watershed accumulation, geomorphology of the lake bottom. And there is a main archives are heterogeneous sediments, geochemical and biogenical sediments, cosmogenic volcanic sediments, exogenic and endogenic fossils, aerosols, and water pollen. In our case, we have only heterogeneous sediments and chemical biogenic sediments, and some exogenic fossils, okay? There is no any traces cosmogenic or volcanic, okay, or volcanic sediments and some pollutants. And radiocarbon dating of lake deposit provides critical chronological framework for understanding Holocene climate and environmental changes. Complexity of organic matter dating is a bulk sediment, including both allochthonous and autochthonous materials. Those materials could contain some old carbon, which was formated in sediments before they actually were deposited in the lakes. And radiocarbon reservoir effect and sediment mixing further impact dating accuracy. There is important to find microfossils remains of plant and other short-living organisms to correct the age estimation. We try to develop age depth model using radiocarbon dates from different materials. And they are aquatic microfetus, it's trapose seeds, insects remain, chronometer, head capsules, and bulk sediments. Identification of discrepancy between this date from the plant and insect material and the bulk sediment In evaluation, the discrepancy are systematic and informative to climate environmental changes at Gatwal Himalayas during the mid to late Holocene. That's our object of the study. That's a nice small lake in northern India, which is at elevation of about 2.5 kilometers, and main precipitation come from Indian summer monsoon, and vegetation is right now. Actually, vegetation is a forest, and this, as I said, this is a closed lake which is actually does not have any input from the rivers and any output with the rivers. The input comes just from precipitation, wherever it is rain or snow, melting snow, and lake level is controlled by temperature, by evaporation of the water. And that's a view from this lake, and I like this picture on the low left corner, which is actually a reflection of the surrounded Himalayan mountains, glaciers actually in the lake. And materials and methods. Okay. Sediment core was recovered in 2018 by under leading actually Dave Parinche, and it was extracted about 380 centimeter core from the depth of the lake of about 5.5 meters. Surface sediment they kind of liquidated, were collected in a plastic tube, and the dense sediments was retrieved in a stainless steel barrel. The core was wrapped and stored at 4 degrees Celsius. And then it came to our lab for analysis. You can see here the materials on the left side, left or right? Left side, you can see the cores. Actually, this brown, it's schematic, but as you can see, core is almost black. That's sediments with a quite high content of carbon. It's vary from 2-3% to about 8-10% of organic carbon. And trapezoids you can compare with a penis. It's about penis size, and chironomid samples on this picture. I don't know where it's pointed. Here. And this size is under 40-fold magnification. Actually, they're very small, very small. The methods which was applied. The first is extraction of chironomid. Yesterday was presentation about pollen extraction with cytometry. Unfortunately, we do not have cytometry, but we have grad students who are able to collect these kind of samples. You can see the sediment. I'm sorry. The sediment, dry sediment, was treated with 10% potassium hydroxide, and it's going through the nylon sieves, and isolated chironomid remains were actually manually picked up from the suspension. There was collected about 2,000 head for each sample. No, as you can see, it was in the final graphites was in a range between 60 and 150 microgram. That was a standard treatment for which we apply actually for sediments and trapezoids. It's ABA treatment, and that's it. And then the samples were combusted with copper oxide and graphitized with hydrogen, and finally measured on accelerator, which I show you on the first slide. Okay? And then it was done radiocarbon calibration and some small modeling using OxCal, and that's it. And what we got? That's results for sediments. And
Doesn't work this.
Doesn't it work? Oh, okay.
If you want to make a mouse.
Mm-hmm. That's lovely. Okay. As you can see, if you look at this model for sediments, at the oldest date which we actually get, it was about 5,000 calibrated years. And at the beginning, the accumulation rate was relatively slow. But about 2,000 years ago, accumulation rate of sediments start to increase. And at about 1,000 years ago, it's actually, it was, I would say, catastrophic, because during 1 meter, 1 meter was accumulated. If you look at radiocarbon dates, they was accumulated at the same time, because at the top date it's 1160 and bottom date 1120. And there is a small inversion also here. What's the reason for that? That's a secret, I think, like, I'm kidding. Okay, and actually, if we look on the history of these sites, about 2,000 years ago, it's people came to this lake and started to do some agriculture work. And at the beginning, it was quite slow, and then about 1,000 years ago, it was active agriculture, which actually initiate erosion and certainly huge accumulation rate in the lake. Yeah, that's a picture of Hieronymus head. And if for Poland was estimation that one pollen grain is about 1 nanogram, our sample is significantly bigger. They are only 50 nanogram, I'm sorry. And the results of Hieronymus, it's also show huge accumulation rate for the same range, but dates is significantly young. If you look, if you remember, it was something around 1100 years. Here we have something between roughly 700 years and 900 years. And that's age model for trapezoids. You remember that's a quite big fragments with the size maybe about 3-4 centimeters. And again, we have the same huge accumulation of rate for the depth from 190 centimeter to 90. It's almost was done in momentarily. But for some reason, this inversion peak has disappeared. And then we decided to look at stable isotopes. If you look for stable isotopes for sediments column, you can see that the bottom has very depleted organic matter. And coming to the top, it's getting some relatively slow enrichment. We compare these stable isotope results with pollen analysis. Green line show concentration of cereal in this sediment, and we can see that after about 500 years, actually starting from 1,000 years, concentration of cereals start to increase from almost below 2% to about maximum 10%, which also indicate, and some cereals is a millet, which is C4 plants. And that's actually confirmed this hypothesis that it's human activity initiated all process and accumulation of sediments. Those two curves show in intersample comparison between red line between trapezoids and sediment, and blue line between chironomids and sediments. And you can see that offset for the seeds, it's very significant. It's up to 800 years. When chironomids, it's relatively slow, less offset. And besides that, if you noted before, the error for chironomids is significantly higher, and it could be in a range of 2 sigma. And finally, the conclusion. The dating of the different materials from the same horizon yielded with a significant different dates, especially after 2,000 years. The radiocarbon dates for chironomids and trapezoids case yielded younger and more trustable age distribution than bulk sediments. Varied dating results across materials suggest different their origin. The high rates of sediment accumulation resulted by anthropogenic activity and development of agriculture, which indicate the initiated erosion and the fast sediment accumulation with old carbon. Results of pollen and stable isotope ratio analysis confirm the increased grass content, including C14 plant, around 10,000 years ago, which explained by also human agriculture activity. The plant and insect fragments give more reliable results, so they were formed at the time of the sedimentation. The sediment deposit could have, say, a memory effect from soil-formated processes and terrestrial slopes. Thank you for attention. But as I said,
perfect timing, Alex. You have 2 minutes for questions, or we have 2 minutes for questions from his time. Questions? Congratulations, I like this.
Yeah, thank you. It's also a question for the first speaker today. When you do this dating of sediments, either with microfossil or insects or whatever, what would you associate as, time included? Because the sediments are not deposited continuously. There is some bioturbation. So what would be the time integration for these samples?
Migration to sediment?
No, integration, like, it is 40 years of sedimentation, because you date an insect, but, it could be deposited up. So there is a time for the sediments to deposit. So what is your estimation?
Example, the rate sedimentation for Hieronymus is 0. Oh, you can say for radiocarbon it's 0, because it's called, other name for this is lake fly. And their cycle is very short. Very rare they live a few days, mostly 1 day or 2 days. And certainly there's trapezids or water chestnut, there's aquatic plants, which is, I think seasons, 1, 2 seasons, maybe 3. But sediments, as I said, that's because there is different type of sediments. It's like githia, and some sediments enriched with clay, which could come from the slope. You see, it's like a funnel. This lake like a funnel working. It's accumulated from a surrounding slope.
Alex, you fit it perfectly in 20 minutes with
Thank you.
no singing, huh? Thank you. So we're moving to the next presentation. We are behind time. J. Pilch. Oh, okay. It's a Polish name. The Belling-Older Dryas Alerot transition and multiproxy paleo record of 2 neighboring sites, landslides.
Good afternoon. Buongiorno. My name is Jolanta Pilch, and today, on behalf of my colleagues mainly from Kraków in Poland, I would like to present the topic on Belling-Older Dryas Alerot transition in multiproxy paleo record of 2 neighboring landslide fens, Kotoń and Kraklowo, which are located in Outer Western Carpathians, southern Poland. This is about the regional similarities and local differences in plant succession, and these are the preliminary results. This topic is a part of a bigger project, which is about the reconstruction of late glacial. Too close, okay? A little bit. It is about the reconstruction of the late glacial period based on the deposits of some selected landslide fens from Polish Western Carpathians. There are several aims of this project, and today I would like to address 2 of them. One is about these differences in paleoecological record between 2 sites, Kotoń and Kraklowo landslide fens, which are located in near to each other, but in quite different hypsometric positions. And also, as we already learned today, the late glacial period is a time of many short-term climatic fluctuations, so we would like to also track these changes in our vegetation record. But first, briefly, what is a landslide fen? So if we take a look on the very diverse topography of the landslide, doesn't work. Then the very significant feature of the topography on landslide are depressions. And these depressions can successively be filled with deposits of some like small lakes or aquatic reservoir, or by peatlands. Or usually we can observe also the transitions between these two types of environment, and sometimes the whole succession between these two forms can be observed. And I forgot to add that in our case, we are investigating mainly peatland deposits, and in this case, these mires, these peatlands, are fed by groundwater, which is nutrient-rich, and these kind of peatlands are called fens. So we are investigating landslide fens. And when it comes about the time period, it is a late glacial period, so the time after last glacial maximum, more or less between 15,000 to 11.7 thousand years ago, so until the beginning of Holocene. And as we can see on this Greenland ice core isotopic curve, this is the time of many short-term climatic fluctuations. On our special interest is older Dryas climatic oscillations, so I will try to address this one shortly today. Study area, as I already mentioned, is outer Western Carpathians, the southern part of Poland. And within this outer Western Carpathians, there are several mountain ranges called Beskidy, and one of them is Beskid-Makowski Mountains. And within this not so very high mountain range, there is Koskowa Góra range. And within this range, there are these two landslide fens located, although actually there are many more landslide fens within this area. But these two are very specific because they have very continuous late glacial sequence within its deposits. So what are the differences in these two landslides? Landslide fens. So Cotton landslide fen is located on the southern part of the massif, and it is located higher with the altitude, more than 700 meters. It is also not much influenced by some continuous streams or like superficial hydrology. On the opposite to Klaklowo, which is located in the lower parts of the massif with the northern exposure, and also there is a lot of streams which are periodical or continuous going through this area. And there are many more differences. For example, that the landslides within which these fens developed, they are also different types, and this is also connected with geology, and this is also influencing local hydrogeology. So there are really a lot of differences, but I will not go much into details now. What is important that when we take a look at the cross sections through these two small peatlands, then in case of Klaklowo, the overall thickness of the deposits, of mineral organic deposits, is 3.7 meters, whereas for Cotton it is 5 meters of mineral organic deposits. Now, materials and methods. There were many multi-proxy analyses done for these deposits of these sites. Here I would like to briefly say about macrofossil analysis, so identification of the plant remains in the sediment. Our basic method for identification of lithological changes was loss in ignition analysis. Also, we did a pollen analysis. I will only briefly mention it here, but I guess that from perspective of this conference, the most interesting is radiocarbon dating and HDEP model. So I will start with these results. So for Klaklowo site, for the whole this 3.7 meters long sequence, we acquired 12 radiocarbon dates, and these dates were based on selected macrofossils. Mostly these were generative parts of plants like fruits, like seeds or needles. But in some intervals, there were mostly like aquatic plants, and there was a challenge because some, like one depth interval, we had to repeat 3 times because in 2 times the age was very much overestimated, and it seemed that it could be because of the reservoir effect of Moses stems, which could absorb this older carbon from this aquatic environment, probably from carbonates. So this was a situation for Klaklovo. These dates here are also presented as calibrated, and based on the 10 dates of this from this profile, the HDM model was elaborated in Oxcal, and this model is challenging and problematic in the upper part. However, this is already Holocene, so it is not the main aim of our interest right now, but in this lower part, although this agreement is not like recommended 60%, still it is reliable. In case, and here also I present the modeled age on the with the time scale and the sedimentation rate calculated based on this data, expressed in millimeters per year. So for the late glacial time, which is here from 40,800 until 11.7, this sedimentation rate differs from half of millimeter per year up to more than 2 millimeters per year. In case of cotton, there were 6 radiocarbon dates, and also this material was more satisfactory for radiocarbon datings. So based on these radiocarbon dates, we created also HDM model, which was less problematic than for Klaklovo, and also within this late glacial interval, it is reliable and has agreement of more than 90%. Here is presented modeled age and sedimentation rate. So the time span is similar, like for Klaklovo, 14.5 thousand years calibrated BP, and we finished our investigation on the Holocene boundary. When we put this data with some lithological results, and here you can see loss on ignition, which says that if there is like higher percent on this curve, it means that there is a lot of more of organic. And already in this case, when we compare it also with this stratigraphy of Greenland ice cores, we can notice that Bolling, Olderdryas, and Allerate transition, this interval which we try to focus on, it is characterized by prevailing mineral sedimentation with only some organic inserts. This is in case of Klaklovo. And what is interesting, Olderdryas climatic cooling, it is expressed within this some organic inserts. I will try to tell more about that in a few seconds. And similar situation is for cotton. Bolling, Olderdryas, Allerate interval, it is also characterized by mineral sedimentation with organic input of organic matter successively increasing upward. And also in this case of Klaklovo, we can see that from the depth of around 260 centimeters, and in case of cotton at the depth of around 360 centimeters. So with the onset of Allerate, there is a change from this mineral sedimentation into peatland sedimentation, sedimentation of peat. So here is some first attempt of correlation. I will skip this now because this is what can tell us about these vegetation changes and what exactly was going on both of the sites during this time we want to focus on. So in Bolling, this mineral sedimentation, it tells us that there was some water body, some sedimentation took place. And based on macrofossil, plant macrofossil diagram, we can see that not many vegetation was actually living in this. So perhaps it was some kind of oligotrophic water body with scarce vegetation. And this is situation for Klaklovo, and the same situation is for cotton. So here we have similarity for this Bolling interval. When it comes to older dryas, for Klaklovo, this lower situated landslide fan, older dryas, it is the time of this organic insert, and probably at that time the water body of Belling shallowed, and some short-lasting fans with oscillating water level developed at that time. And what is interesting, during that time at Kotoń, the water body didn't disappear, but it was already inhabited by some aquatic plants. And these aquatic plants were mainly dominated by Harace, Batrachium, Putamogeton, the whole succession. As you can see on the diagram, this red rectangle shows us that actually this is the only time in the history of this peatland of Kotoń that this kind of aquatic succession takes place in such a remarkable way. Although Kotoń is not worse with this case because there was also some aquatic plant succession, but not at the same time. It occurred later during the climate amelioration of Alleret. And also it is on the bigger scale. These are the difference. Now some similarities, and these similarities are about observation of vegetation changes, but on a regional scale. If we move a little bit ahead from the site of the peatlands, in the neighborhood of these peatlands, in case of Kotoń, there was like a steppe tundra vegetation formation prevailing, which we can conclude from, again, macrofossil diagram, because there is a lot of representatives of species of dry and open land habitats, especially Dryas optopetala. It is some like indicator of also cold climate. So probably some steppe tundra environment occurred around Kotoń, and what is interesting, also around Klaklovo. So we can imagine that at the time of all the dryas, this steppe tundra was spreading over at least our massif of Koskova Góra. When we move to Alleret, there is another similarity which can be observed, that with Alleret, the boreal forest appear in the site of both fens. For Klaklovo, around 13,800 years Cal BP, we can observe Pinus betula pubescens, so birch, immigrating to this site. And 30,650 years Cal BP, it is also Pinus sylvestris. So the boreal forest appears here, and the same time of this arrival of these two species occurs at Kotoń site. So we can also see that these regional changes of plant formation occurred at two investigated sites synchronously. And this is preliminary conclusion. So actually what I already said is written here, so maybe I will just briefly summarize that we can compare these two sites thanks to this absolute chronology developed based on this radiocarbon dates, and we can see that there are some similarities, like for example, Belling water body which is not inhabited by much aquatic life. Later we have some similarities with appearance of boreal forest and also occurrence of steppe tundra during older dryas in both sites. But there are also differences, like more local one, that the aquatic plant successions within these water bodies occurred in both sides, both of the sites, but not at the same time. First, it developed in Kotoń, and later with Alleret climatic improvement also in Klaklovo. So these are the things we will try to explain why it was this difference. So thank you for your attention, and if there are any questions, I'm happy to answer. I'm not prepared for singing, but if you sing, I can sing with you. But challenging also.
Okay. Now you presented such a tool of radiocarbon that it's for understanding of the vegetation. So, yeah, very, very impressive work. Thank you.
Thank you. Okay, so thank you.
Thank you. It looks like you guys have the timer from the computer because her talk is still 2 minutes more. But we will win 2 minutes. The timer has to go to 0. Yeah. We have presentation by Jordan Pali, Italian presentation for the closing of the session. Radiocarbon dating and a tree longevity. Sounds good.
Yeah, thank you. So, radiocarbon dating and tree longevity estimates. In this presentation, I will give a brief introduction on the state of the art on radiocarbon dating and as well tree longevity estimates also with other techniques. And then a focus on 4 different Italian case studies that we developed with collaboration with the CEDA laboratory here in Lecce. So, but before I start with this, with the data, with the presentation, I'd like to introduce why is it important to assess tree longevity. There are 3 main reasons. The first one, of course, is the conservation biology, because ancient trees harbor a unique biodiversity from their genetic heritage to the habitat they create. They themselves are habitats to several species, so it is important to know their age and to set appropriate conservation measures. The second reason is that they are natural archives. They record a set of environmental changes from temperature changes, water availability, also other aspects, including the local cultural and landscape history. And also, sometimes they record other atmospheric events like cosmic radiation and so on. So they are exceptional natural archives. The last one is that it's for ecological planning, because ancient trees are long-term carbon reservoirs. So it's important to know where they are to conserve and to set appropriate ecological planning. And also because they accomplish, other than carbon reservoir, the service of carbon reservoir, many other eco-services that is important to preserve for future generations. So knowing where they are is fundamental to set optimal conservation policies. How to assess tree longevity? There are basically 2 methods we can apply. The first one is the measurement of tree rings, that is also known with the term dendrochronology, which has the strength of being accurate, because with this method we can measure tree growth and tree age at one resolution without uncertainties, but has the weakness of being not applicable to most of tropical trees. And this is not applicable to trees with old or rotten stem. That is a typical condition of very ancient trees. So this is a big problem for us that wish to know the age of huge and ancient trees. The second method is, of course, the radiocarbon dating, which has the strength of being applicable to every tree, in every condition, in every biome, in every health condition, as long as there is a material to sample, of course, inside the tree. But it has the weakness of sometimes large age uncertainties, and also the lack of information about tree growth variations over time. Most of studies about tree longevity have used the tree ring measurement, dendrochronology. Here I'm showing a recent review of public domain tree ring series, an analysis of public domain I mean, three ring series in an online database that shows the distribution of age between angiosperms, that are flowering trees, and conifers, that are trees that produce cones like pine, firs, and so on. This review indicate that tree-ring studies that conifers might get extremely old. That's something that we know, with a maximum tree age of 660 years, and 22 species around the world that can exceed 1,000 years of age. Angiosperm flowering trees are way less longeval, with a mean maximum age of 229 years, and just one species that can exceed 500 years of age. This is based on tree ring measurements. But if you look at radiocarbon dates of our review of radiocarbon dates on trees, we find that angiosperm can actually exceed 500 years old. 24 species, we found 24 species that can exceed 500 years of age, with a mean maximum tree age of 37 different species of 681 years. This means that radiocarbon dating opens up new frontiers in the study of tree longevity. So this is the general framework. Now let's go in detail on 4 Italian case studies. The first one is that of Cecil Oaks in the Aspromonte National Park. We went there for several years. So we sampled 23 trees, very large trees up in the mountain. And this is what we found, that of all the sample, 14 trees, that is the 50% of the sample trees, exceeded 450 years of age. 450 years was the maximum lifespan of this species indicated through tree rings studies. So thanks to radiocarbon dating, we found many of them, more than half of our sample, that exceeded that threshold. And the oldest one was dated at an age of more or less 900 years old. And today, this tree was called Demeter by us. And this today the oldest reached that age. But then to try and fill in the gap from the inner part of the stem, we took some cores from the exposed roots. And to synchronize the two signals, from the root, the one from the roots and the one from the stem, we used radiocarbon dating. So thanks to radiocarbon dating, it was possible to match the two chronologies and to push back the age of Idulus of 166 years. And the final age resulted 1,230 years. And is today the oldest tree, which was scientifically dated, dated through scientific methods in Europe, so the oldest trees of Europe. The third case study is that of ancient fruit trees of Basilicata. We went in Basilicata, in the cultural landscape of Basilicata, and we sampled a lot of different fruit trees, different species, olives, chestnuts, pears, mulberries, apples, and so on. In this case, we applied both methods, tree rings and radiocarbon, depending on the condition of the tree. If the tree was in healthy condition, we could take the core, we measured the age by tree ring measurements. When the tree was huge or old and so on, we took a sample from the inner part of the stem and sent them to the CHEDA for radiocarbon dating to know the age. And what we found is that thanks to radiocarbon dating, many of these species were very, very ancient. For instance, I'm showing here in the table, we had chestnut, mulberry, and olive trees that exceeded 600 years of age, and the pears that reached almost the 500 years of age. And here in the graph on this side, I'm showing the differences between the result we got with tree ring measurements and those coming from radiocarbon results. And it's very visible the differences between the pool from the radiocarbon, from the tree ring measurement and the ages we got from tree rings. The last one, the last case study, okay, is that of Holm Oaks in the Monte Cristo Island. Monte Cristo Island is famous because it was mentioned by Alexandre Dumont in its novel, The Count of Monte Cristo. It is an island in the middle of the Mediterranean Sea. It's completely uninhabited, and it's the homeland of Holm Oaks, very monumental Holm Oaks, that we are still analyzing. This is still an ongoing, an in-progress project. And for now, we measure the age of some of these very big trees. Of course, it is impossible to take wooden cores for tree ring measurement because these trees are huge and are very rotten in the inside. But our preliminary results indicate a mean age of 470 years, with the oldest individual dating 741 years. And we are still analyzing them. We are going them 1 or 2 times a year, getting more cores, but it's very hard to walk in this island, and we are pretty sure going on with this project that we can find something very, very exceptional because these trees are very huge and beautiful. So to close, to sum up with this brief presentation, I shown how radiocarbon dating actually help expanding the longevity of several species beyond the current understanding, beyond what we know about the maximum lifespan of this tree. Radiocarbon dating is especially successful in case of ancient trees with characterized by natural wood decay, sampling difficulties, or unclear definition of annual ring. That's something which characterizes given species. Angiosperms, in particular, flowering trees, resulted in average twice the age older compared to tree ring studies. Using radiocarbon dating, we found some of the oldest scientifically dated tree of Europe. And yes, thanks for your attention. Fa pensiero.
Thank you very much. I envy Gianluca being so close to these trees. But I bet there are other countries like Poland and other countries, they have also those trees. Yeah. So questions. We have 10 minutes for questions. Wow.
Fine. My question is about Italus. I don't know if I pronounce properly. It's related actually with the dendrochronology portion. How was overlapped the dendrochronology of the root with the width growth of the tissue? Because I don't know how a root will grow annually as well.
Yes, because that root in particular was exposed, so it kind of grew like the stem, because it wasn't in the soil, it was outside, so the growth was annual, and we used radiocarbon dating to find a matching point, and then we synchronized with the statistical technique. So we used the statistical output to find the perfect match and to anchor the two chronologies.
But the tissue formation is annual as well?
Yes,
for
yes,
the
yes.
roots?
Yes, in that case, yes, it was annual, the ring formation of that kind of root.
Okay, thank you.
And there's another question.
Why the dendrochronologists that gave such a short lifespan for the tree? They never actually measured a long-lived tree? Did they miss rings for so many?
Yes, the fact is that yes, you can you don't actually have the wood inside the tree. So the more ancient the tree is, the less wood you have in the inside. So you don't have the sample. That's so when we go there and take the sample for radiocarbon, we usually go down to the color, because in the inner part of the stem there is almost nothing left. So it's impossible to do a core for dendrochronology measurements.
It's not a question. I know 3,600-year-old in Chile. It's called Fitzroy's cupressada. And Antonio Lara made a nice job on that. He's a dendrochronologist and he did compare with radiocarbon.
Yeah, thank you.
Pasha behind.
Okay, I have a few comments. First of all, thank you for a very, very interesting presentation. May we go back to the one previous slide? Just one. Yes. No, only one.
This one.
Have you collected samples along the slope or across? Because it's for stable isotopes, for the measurement of dendrochronological research, it is important. So this would be the first question. The second, if we can go back.
Sorry, I didn't understand the first question. If I collect
Is it how you collect the samples? So
yes, this is
along the slope?
this picture. This is how I collect the sample for dendrochronology. This is a pressure borer.
Yes,
So
but there is compression wood or if it is
yes,
along the
it might
slope.
be. Yeah, it might be. Yes.
Okay, so this is one. Can we go back a little bit? Okay, once more, please.
One more.
Okay, here on the which we can see with the purities. My question is, because it looks like two groups of the points. There is a linear correlation for DBH and the age. So I'm a little bit worried to put really a linear correlation, because it seems like a group in like the black dots. Like
yeah,
one
maybe
group.
they
So
are not.
if you give another points, every time you will receive a line. And the third question is just about, in general, about the chronology. Do you use the ring widths, so you just measure how many millimeters it is, or you convert it to the standardized, like the indexes in the tree rings? Because then you probably you observe it that at the beginning the width is much more bigger than at the end. So if you remove this trend,
Yeah,
you
we
have
usually.
indexed chronology.
Yeah, we usually detrend the series, and when we compare the two series, for example, to synchronize them, we don't take account of the wind of the series, but only of the peaks of the development of the series for synchronizing purposes. If I correctly understood your question.
Well, if there is more questions, but maybe from her, because there is more questions from other people. You gave us time. We have still 5 minutes of this session, so sorry. You have to answer them.
Okay, thank you. Just a curious question. I saw you have a big tree and you use the core, and I suppose you use 12 mil diameter to core it, because if you use 5 mil, it's very difficult to core, right? Yeah.
Yeah.
And how strong are you? Because that is a lot of pressure, right?
Yeah.
In order to core it, and yeah.
This is why they hired a big boy like me. Yeah.
Okay. And how many core in the tree in order to get the center? Because the center maybe not, in the middle of the tree. Sometimes it's,
Yeah, sometimes we just take the center the first time. Sometimes we need to do 2 or more cores, but we don't usually drill many many times a tree, also because we care about its conservation. So we don't do more than 2 or maximum 3 holes.
Okay, thank you.
There's one more question. No. Okay. Can I ask? Are the trees secret? Are they open to public for people to see? Because
Yeah, most of them yes, but the 2 oldest, the 2 very big, they are not. Yeah, they are not because they can't want to avoid people go there and damage them. Yeah.
Okay. Thank you. Do we have more questions? Well, he said he doesn't. Yeah, he said no. Oh, Walter, do you want to ask your question? Well, no. Okay, then I will ask one more. How, if you don't drill? I mean, we did it great with time. We still have 2 minutes. If you don't drill the, if it's like hollow, how do you take the sample from inside?
We try to go into the stem from an aperture and take the sample by hand or with that tool. But if the tree is closed, we cannot take any sample for the radiocarbon purposes. So we cannot drill it because it's already inside. We cannot take any sample. So the age of the tree that's remain a mystery. So this is why there are many trees that are presumably very old, but we actually don't know the age.
And if you go, if you go in, but then you have like a camera to see inside?
Yes, yes.
Okay, great. Okay.
Thank you.
No more questions. Thank you to all the speakers of the session.
Welcome at this last talk of this. Welcome at the last talk of this this session, and it's a real pleasure and honor to have here Professor Paul Arthur. And I'm saying just a few words about his life and his professional achievement. He was born in the UK. Then he graduated in archaeology at the Institute of Archaeology of the University of London. Then he got his PhD in archaeology at the Institute of Archaeology, always at the University of London. He has been associate professor in medieval archaeology at the University of Lecce, now University of Salento. Then since 2005, since today, is a full professor at our university. He has been a principal investigator, I cannot list all of them, a lot of projects or national relevance, such as I'm just mentioning the projects which are running at the moment, like the Byzantine heritage of Southern Italy settlement, economy and resilience in changing territorial and landscape context, and again another project populating Byzantine Southern Italy. We were just discussing that a very important conference about Byzantine archaeologists that ended this week. He was the chairman of this conference. He has been director of our postgraduate school in archaeology of our university. He is in the editorial board of several journals. I cannot mention all of them. So it's I'm very pleased, and it's a real honor that he had time to join us and talk us something about a brief history of the medieval Lecce. You know where we are, and so it's not by chance that he is here. He was also responsible of the archaeological excavation you have seen in the entrance of this wonderful monument. So thank you, Paul, and the stage is yours.
Thank you, Gianluca. Puoi raccontare. Well, good evening, good afternoon to everybody. I hope you understand my bastard English after living in Italy for 40 years. Occasionally I start to forget words in English and think, how the hell did I used to say that many years ago? But I'm speaking in English, so if there's anything you don't understand, please stick your hand up and say, could you please repeat yourself? I think my diction is quite clear, so you should understand everything. Thank you. Just a couple of words. First of all, of course, I want to thank Lucio and Gianluca for having invited me to come and speak to you today. It's a great pleasure and a great honor. It's been 5 days of constant lectures because, of course, yesterday I finished my international conference on something totally different. But it's always great to speak with colleagues, to exchange views and maybe have some sort of important feedback. Of course, I'm not going to speak about radiocarbon dating, but I've been using it for a long time, ever since I got to know Lucio. So he's been helping me to build up a Middle Ages. And when I arrived here, the Middle Ages, I don't mean Middle Ages age-wise, I think I'm not even middle-aged, I'm old. But the ancient Middle Ages, the medieval times, when I arrived here, there was hardly any idea what had happened because there's some textual sources, but the countryside, the sites, the finds, they were all sort of floating around in limbo. So we needed to use radiocarbon dating and other forms of scientific analysis to try and pin things down. But I'm not going to speak about that this evening. What I'm going to do is give you a lecture, which I hope won't last too long, otherwise you'll all fall asleep, on the walls of Lecce, because in the from about the year 2000 to 2018, I spent a lot of my time actually digging in Lecce. It was a period of money coming in for restoration work, and so I restored a couple of the major monuments as an archaeologist. I'm not the person who actually does the physical restoration, but I'm the scientific advisor, suggest what people do, try and read things as restoration is going ahead, and try and get some sort of meaning out of what we're seeing. So I'll try to express what's in a wall with you today. Of course, we're in these marvelous walls here at the moment, and this is part of the project that I worked on. And when you all go out, don't fall in the big hole in the courtyard. That's my fault. I wanted a big hole in the courtyard, and it's still there, thank goodness. In fact, I want it even bigger, because that's where a lot of our story is coming from. But let's start from the beginning, if I can get this thing to work. So here we are, Lecce. Lecce Lupiai. Lupiai was one of the many, well, I think there must have been over 370 Roman towns in Peninsula Italy. And Lupiai was just one of many of them, not certainly one of the most important, but nonetheless a very interesting town. We can't do much archaeology within the town because it's all built up at the moment, but every now and again something can be done, and some of you may have seen some of our ancient Roman monuments, such as the amphitheatre, which is right bang in the middle of Piazza Sant'Oronzo, the theatre, the Roman theatre, and then bits and pieces. And in this slide you can have a sort of bird's eye view. Well, I think the bird's about to land, but you can see a view of the theatre and the amphitheatre and the city walls around. You have a plan of Lecce, not very large, 50 hectares. Just to give you an idea of the size, I think Pompeii was around 80 hectares, Ostia about 190 hectares, and my own little city of London, that used to be called Londinium, 330 hectares. So Lecce is a small provincial town, but it's important. It's important especially because it lies in the heel of Italy, so it's a conduit, together with places like Brindisi and Taranto, to the East, or people from the East coming into Italy and into the rest of Europe. So that's I think its main claim to fame. It has some famous people, as Quintus Ennius, a poet who was born here and wrote here. And you can see the sort of statues that come up, I mean, with the sort of thing that grace all Roman towns, otherwise they're not very Roman. So we start off with a 50-hectare town, which isn't bad. Hard to calculate exactly how many people, but certainly a few thousand people. And then we move on to the end of what we call the Roman Empire. I mean, a lot of you will have heard about the fall of the Roman Empire. You may have read Edward Gibbon's books on the fall of the Roman Empire. Anyway, in 476 AD, after Christ, the Roman Empire in the West collapsed. It collapsed because it was invaded, or let's say it collapsed because some generals, in particular this person called Odoacer, who worked with the Romans, decided that he would take power. He was from outside of the empire, and he deposed Romulus Augustus, who was only a young boy at the time. They said, I am now the person in charge of the Roman Empire in the West. It was no longer the Roman Empire, of course, by that time. And poor Romulus Augustus was stuck in the castle, this lovely castle here. It's a very atmospheric photograph. Is Castel dell'Ovo. Some of you may know Castel dell'Ovo if you go to Naples, because it's at Santa Lucia, jutting out into the sea. You know, there's a very good fish restaurant there, by the way, so if you want fish, go and eat at the restaurant at Castel dell'Ovo. Castrum Lucullanum. So basically the empire in the West ended, and it became gradually a Gothic kingdom. No more Romans, Goths. The idea of the Roman Empire continued in the East, in a place called New Rome or Constantinople. I'll show you a slide in a second. So the fulcrum, the center, let's say, of attention of what used to be this incredible Roman Empire moved east to Turkey, to Asia Minor, to become the Byzantine Empire. Interestingly enough, the Byzantines never called themselves Byzantines. If you went up to a person in Byzantium and said, oh, you're a Byzantine chap, aren't you? He'd look at you and said, what are you saying? I'm Roman. They considered themselves Roman as well. So in a sense, the Byzantine Empire is a continuity of the Roman Empire with a shift in geographical capital. So the Goths, Ostrogoths, took hold of Italy and the opposite Adriatic coast and other places. And in the 530s, so we're talking about the early 6th century, a certain Justinian the Great from the Ravenna Mosaics, thought, well, now is the occasion for me, he was a very ambitious man, now is the occasion to reconquer the Western Empire. He was in Constantinople. He said, I'm going to take back what we've lost. And so he started a war. The war was called the Justinianic War. It was a 20-year war. It's a hell of a long time to fight, 20 years. A 20-year war, but it wasn't entirely his fault, because in those years, especially in the year 536, there was a catastrophic worldwide event which really, as we say in England, put the spanner in the works. It rather screwed things up, if I may say, for Justinian. So not only do we have war, we had war, or they had war, we missed that war, we have other wars. They had plague, bubonic plague, which is rather nasty if anybody knows about it, 3 days and then you're kaput. And abandonment because people were dying all over the place, either being killed or dying of the plague, or running away, hoping to find somewhere where they could live with at least a little bit of safety. So that's why I have these slides, and one of my favorite slides is that of the black rat looking at the piles of bodies dead from the plague outside of a Roman town. So it was a real mess in 536, and the mess was what really made the Justinian War last for 20 years. it was going to be a quick war. But then when you have things like plagues and people dying all over the place and other strange phenomena, it does make war a little bit more difficult to achieve. All this happened because of things happening on the other side of the planet. Well, some people say that even Iceland has something to do with it. I mean, there's that lovely volcano in Iceland that I will not pronounce because I can't pronounce it. If anybody's from Iceland here, they can pronounce it properly for me. But apart from the volcanic activity in Iceland, there was a volcanic activity in Central America, at El Salvador, this incredibly large volcano called Ilopango, which exploded in 432, so a little bit before that fateful year. Then another one called El Chichon around 546. I mean, these were massive volcanic eruptions that were obviously part of some sort of almost global instability of our world, which brought about a hell of a lot of, sorry, I'm very colloquial at times when I speak, a lot of big problems for the world, including, for example, in Central America, what appears to be the demise of the famous Maya civilization. Well, we were a bit happier here because there was no direct volcanism in this area. But you see, when you have that sort of volcanism, as many of you probably know, you have problems of ash in the air, of the sun being blanketed over, the drop or lack of photosynthesis, so the difficulty of plants growing, and with less plants growing, the difficulty of animals eating, and of course, weather conditions, colder climates that make animals living in cold places say, oh, this is cold, I must go south where it's warmer. And so you have migrations of animals, you have all sorts of structural changes, systemic changes to the world. And one of these was the movement of the rats, of the black rats, the Rattus rattus, that carried the plague, because they came apparently from places like perhaps Mongolia and Central Africa and moved into the Mediterranean, where they said, oh, well, this is a nice place to live. Except moving into the Mediterranean, they took with them the bubonic plague and everything that goes with it. So, abandonment. Well, abandonment is a consequence. It's a consequence of insecurity. It's a consequence of people, so many people dying that you could no longer manage your infrastructures. I've just put up 2 local towns, local Roman towns, because anybody who knows Puglia can just drive up the road and see Ignazia, which is on the coast, or Herdonia. Both Ignazia and Herdonia are abandoned Roman towns. At a certain stage, the people could no longer live there. They just went away. And the scale of the fright, I think, of abandonment, of getting away, even led the bishop of Ignazia to lose his precious gold ring, which has a representation of the Holy Sepulchre in Jerusalem on it. I mean, we don't usually find gold rings like that in archaeological excavations. We're not usually that lucky. But this bishop, of course, running away or being cut down, lost his ring. So it was a period of great demographic regression. Now, as I said, in this whole period, the center of attention had moved from old Rome, Rome in Italy, to New Rome, Rome on the Golden Horn, on the Bosphorus in Constantinople, today known as Istanbul. And here we have the perhaps one of the best known Byzantine emperors, Justinian, although this is from a mosaic that you can see in Italy, in Ravenna, because Ravenna was his main headquarters at that period in Italy. So now Italy was reconquered from the Ostrogoths in a very, very sorry state, but Justinian tried to make the best to try and restore the country and the tax base, the monuments, population, and what have you. But unfortunately, things don't always work out the way we like them to. Well, I told you about the Justinianic War. I told you about the Odoacer and the Goths taking power in Italy, and then about Justinian trying to recapture Italy and spending 20 years of his life managing, but just managing. And only a few years after the end of his recapture of Italy, another group of people decided they were going to invade Italy, the Lombards. Now, the Lombards came from the far north. They were originally from Scandinavia, and from Scandinavia, during the centuries, they moved down through parts of Germany and the Czech lands and into Central Europe. And in the end, they settled in the 5th and 6th century in the great Hungarian plain, which is the westernmost part of the steppes that stretch all the way to China. Now, the Lombards were nomads or semi-nomadic people, and the Lombards, probably in this uncertain climatic times, I like to think that they said to themselves, well, why on earth should we live in this cold, wet, soggy Hungarian plain when if we go a bit further south, there's some nice, warm, bountiful places to live in called Italy. Let's move into Italy. And they did. So we have the Lombards moving into Italy, and, well, thank goodness Justinian had died, so he didn't see that part of the crisis. But his successors had to fight these very sort of unruly nomadic people moving into northern Italy, and in the space of 3 years, crossing from the northeast Alps there, which you can see in green, crossing into Italy and getting down all the way south to Benevento. So in 3 years, they had managed to invade about 1/3 of the peninsula. Now, I reckon that is because the Lombards hadn't suffered so much as the Byzantines, who had to fight for 20 years. So in a sense, they just walked into Italy. Very, very interesting now. There are some cemeteries being excavated in northern Italy by some of my friends and colleagues where they've got large-scale genetic analyses being done on the people found in the Lombard cemeteries. And we're getting incredible information on links between families living in Hungary and families living in northern Italy in the 6th century. We can actually start to plot the movements. Anyway, let's not get fossilized with the Lombards. The Lombards in this map are green. The Papal States managed for some time, until the mid-8th century AD, to remain the Papal States, a sort of independent Byzantine duchy. And then there were other bits and pieces in red that remained Byzantine. But as you see, the empire in Italy becomes a sort of series of islands with Lombards all over the countryside. And where we are now here, we're basically in a frontier area, because by the later 7th century, the Lombards got just a few kilometers north of here, between Brindisi and Lecce. And so Lecce was suddenly out on a limb. I mean, Lecce was already suffering as a city. It was small, and it suddenly found itself in a frontier area. Can you imagine a small town, 50 hectares, but with a lot less people now, trying to hold a frontier against these Lombards who managed to conquer 3/4 of Italy? Lecce becomes a frontier site. Now, this is very important for our walls. I'll show you why. This is it's not the amphitheatre in Lecce, it's just a lovely reconstruction of an amphitheatre being burnt, being destroyed. It makes me think of the early medieval chaos that was going on. But what they did, the Byzantine government, was to create a series of refuge sites. Refuge sites means we can't hold on to something as big as 50 hectares or even 20 hectares. So we'll build smaller fortifications, or we'll go and live on an island where it's hard for people to get to us, or we'll go and live right on the top of a mountain, a hill, so you can sort of look down at them and say the things that sort of Monty Python says to the conquerors, you know, from high above, take fun of them, make fun of them. Refuge sites. Now, Lecce has its own refuge site, I'm certain. The town was too big to be held by the forces, but the amphitheatre was not, because the amphitheatre was small. You've seen, I hope, and if you haven't, you will see the amphitheatre. It's a good-sized amphitheatre, but it's very small compared to the whole extent of the ancient Roman town. And the amphitheatre of Lecce would be just one of the many amphitheatres throughout the ancient world that were converted into refuge sites. And here are a couple of examples. Many of you, I think, will know Lucca. Lucca was an amphitheatre. Now it's called the Market Square, but you can see how it was an amphitheatre and how the spaces have been occupied by houses, by shops, by storerooms, so it now becomes a quaint oval market square. If anybody here is from France, they will know about places like Arles, well, not only Arles, Tours as well, and various other towns where even there the amphitheatres have been converted into refuge sites. That is, the big town became a small settlement on the amphitheatre. Now, I'm sure this happened here in Lecce as well. We don't have any historical documentation. It's just a matter of putting 2 and 2 together and coming out with 4. That's a lot of what archaeology is about. You know that archaeology is not an exact science, but works a lot with statistical probability. So we have here 2 aerial photographs of amphitheatres. On the left, you have the one in Lecce. On the right, you have the one in Catania, Sicily. And both of them have churches along the main axis. San Biagio, St. Blaise in Catania, and St. Mary of the Grace in Lecce. Now, that is not a coincidence. That is what happens typically when a Christian population moved into an amphitheatre to make it their new refuge site. They needed a church because the church was one of the greatest powers of the time, if not the greatest power of the time, far more than secular, the spiritual power. Because the spiritual power, I mean, the secular power, you can say, you know, please help me, government. I don't have any money, I don't have this, I don't have that. And they say, well, don't worry, we'll pass a law, we'll do something sooner or later. And they'll say, oh, no, I can't wait. Then there's spiritual power, where with your faith, you think, well, things will work out all right. So the saints were fundamental. And so what we have this is a reconstruction of the amphitheatre of Lecce, which I've drawn up, and I've actually found that there were 2 centres of power on the 2 sides of the amphitheatre. Under the Church of Santa Maria della Grazia was the spiritual power, and under the buildings on the other side of the amphitheatre, now covered, or partly covered, there was the secular power, a place called l'Isola del Governatore. The arena itself remained probably open as a public space for meetings, for markets, and the town of Lecce in Byzantine times, to me, was that oval. So, I had to put this down because you know my surname is Arthur, and I like to play around with my surname Arthur. I like to think that my great-great-great-great-great-great-grandfather to the power of I don't know what was King Arthur, but he didn't leave me anything at all. But it doesn't matter, I've got the name. This is the round table of King Arthur in Britain. He was a warlord of early medieval times. And below we have a Roman amphitheatre in Britain, a place called Cirencester, lovely place, very nice, charming place to visit, which was an amphitheatre. And there is a thesis, an idea, that the amphitheatre of Cirencester, which was Roman, was converted as well into one of these refuge sites for warlords like King Arthur. And so the idea of the Round Table comes from the idea of having assembly sites in the arena of amphitheatres. Makes a lot of sense, but we can't prove that at the moment. Anyway, moving through the centuries, otherwise we'll never end here, in 1071, the Normans captured the city of Bari. Now, by 1071, Bari was the center of Byzantine government in Italy. Bari fell, capitulated, and with the capitulation of Bari, it put a stop, an end to Eastern control, Byzantine control on this country. That was the end. Anything else was just a matter of commerce between East and West, but now it was firmly and squarely Italy in the hands of, well, I would hardly call them Italians, but certainly not Byzantine. Lecce fell a bit earlier, a few years earlier, in 1055. The Normans came, they established their power by building a series of forts, and by this time, we're talking about the 11th century, they could no longer build the massive stone forts that the Romans could build, or even the massive stone castles that later medieval people could build. In the 11th century, forts were mainly built of earth and wood. So here we have below an original document, which is part of the Bayeux tapestry. If anybody goes to Bayeux, actually goes to Caen in Normandy, northern France, they can see this incredible tapestry, 50 meters long, which is 11th century, and which tells the story, almost as though it were a cartoon, tells the story of the capture of Anglo-Saxon Britain by the Norman William the Conqueror. 1066. So really, the capture of Britain was contemporary to the capture of southern Italy by the Normans. So I like to use the Bayeux tapestry as an example of what these people were like. And you can see in this illustration, which is small town in France, built as what we call a motte, in earth and stone, not much stone, wood, which is like the motte that I have reconstructed in the big illustration there. So that was the first sort of thing they did. But they couldn't just continue with such relatively flimsy fortifications. These fortifications were fortifications needed to capture the countryside, to move through the countryside, so they could subdue towns and villages and what have you. Sooner or later, they needed to build serious castles, which they would start doing in the 12th century. Now, that's always a bit of a problem to find 12th century Norman castles. You see, the big problem with early built castles is that the castles usually have... So what happened? Well, here's a photograph, an aerial photograph of where we are. We are in this long sort of room next to the Red Tower on the right, which is just there, just behind us, the so-called Torre Mozza, which I think you can probably see afterwards if you want to. It's the best preserved medieval part of the building, is that tower there. So here we are. These are all the excavations I did in the space of about 20 years, trying to dig as many holes as possible until I think either the town council or some tenant says, you can't keep on digging holes in the castle. So, well, I haven't dug it all up. But I've got enough information to be able to say what happened. So, you see, now, it's not a coincidence that the castle of Lecce, where we are, lies less than 100 meters away from the amphitheater. Now, if the amphitheater was the Byzantine fortification because the rest of Lecce was just too big to be defended, well, it makes a lot of sense that when the Normans took finally the amphitheater, they said, well, we're now going to build another fortification next to the amphitheatre, probably destroying much of the amphitheatre. It took them about 100 years to do that, but they did that, and that is why amphitheatre and castle in green are next to each other. You take 5 minutes just to cross the road, and you can see the amphitheatre if you haven't seen it. So from the 12th century, this, where we are now, becomes the Norman castle. Now, that was debated for quite some time. Until archaeology came along, it was debated who built the castle, because there is an historical document that talks about the Castrum Lici, which would be the fortification of Lecce, which dates to 1241 to 1246, which would not be of Norman times, but 100 years later. But we don't have any other surviving documents for that period. So it's not a demonstration that it was built then, it's just a demonstration that it existed by 1241, 1246. But it could have been built a lot earlier. So we started digging the hole in the courtyard down here, and in the courtyard, as you will see, there are lots of walls, which to people who are not archaeologists will probably create a lot of confusion. Why is there a wall here, and another wall there, and a wall there, and a wall there? What's it all mean? But, of course, we date our walls through various systems with our stratified layers, pottery, coins, and what have you, and I can guarantee that more or less where the arrow is, we found what we call Norman contexts. That is, we found layers of soil and some rudimentary walls that are, without a doubt, are mid-12th century. That is 100 years earlier than the document, and therefore of Norman date. So I can now quite happily say that this is the Norman castle of Lecce, and then it continued until today to be the castle of Lecce. But the Normans, probably a certain King Roger II, was the instigator of the castle. So we dig, and here we go, where we can see some Norman remains. Now, the Norman remains are perhaps the more wishy-washy remains that you can see. I mean, the nice big wall at the top is not Norman. That's 100 years later. These sort of dry stone bits of wall beneath, they're of Norman date. The pits, they're of Norman date. You see, nothing really monumental, greatly monumental, but important because, I mean, remember that earlier they were building these sort of artificial mounds, so it's a step forward in the right direction for construction techniques. Here we have a Norman room. You can see the walls there, not the upper walls, the lower walls on three sides, and that pit. They all belong to Norman date, as here I've written it down, Roger II, probably between 1130 and 1158. So that's the middle of the 12th century. Now, they were fascinating for us because they're telling us something new about the history of Lecce. They're telling us something new about the history of fortifications and architecture of over 1,000 years ago, and from what we find in the soil layers, the dumps that are contemporary with the constructions, we get a lot of other types of information. For example, we found a lot of burnt grain, so we know that there was a storeroom there, and the grain was probably burnt because it has holes from weevils. So somebody had stacked a lot of grain for the Norman garrison, and it was spoiled through weevils. So they burnt it and threw it away. We also found a lot of beans, fava beans, ficha faba mino, which are those beans there, which are more or less this sort of broad bean. But the interesting thing is that this type of bean has a moment of evolution towards the second half of the first millennium. So we're talking about Byzantine times, but we must always think of the Arabs as well, who were in Sicily. Now, in this period, there was an evolution. Now, we're not sure who was responsible for the evolution of the bean. I mean, basically, through interbreeding, the bean gets bigger and bigger, so it's more productive, it's more useful as something to eat, something to use. And some people suggested, well, perhaps the Normans actually introduced the bigger fava bean. Now, we don't have enough archaeobotanical evidence from other parts of Europe at the moment to be absolutely certain. But it would be interesting if that was so, because I can't just see the Normans saying, well, we want bigger beans. It would have been more than that. It would have been, we want better legumes that can help to fix nitrogen to the soil, thus making the soil better for cultivation. I mean, basically, it would be a strategy for an amelioration of agriculture, which makes sense. Anyway, that's something we're exploring at the moment. So, then what have we got? Well, you see at the bottom of the big photograph, you can see the Norman pit that I showed you earlier on. Now, the Norman pit, at a certain stage, was backfilled. They filled it with rubbish. And then they started throwing layers of rubbish above the pit to make these horizontal layers. Now, in one of the horizontal layers, there are a lot of roof tiles, which suggests that they had demolished the Norman structures to build other structures, to renovate, let's say, that part of the castle. And, well, one of my luckiest students, a girl called Marisa, she seems to be the lucky one of the, she's the sort of student you must have on an excavation or in a scientific experiment, because she's always the one that will find the right thing to do, or, you know, and then you have your eureka moment. And so she was just digging away and said, oh, Professor, what do you think about this gold coin? I said, gold coin? Yes, look, there's a gold coin. Ah, fantastic. So I looked at the gold coin and said, oh, here's another, and another, and another. And in the end, she passed me 5 gold coins, which are these 5 coins. 3 of them are perfect. 2 of them have been cut down, because in medieval times, there were the coins, if they were gold, sometimes silver, they would be cut down because, of course, it was the weight of the precious metal, of the noble metal, that counted far more than what it says on it. I mean, it could say €1, but if the metal's worth €10, who the hell cares whether it says €1 on it? They'll cut it down instead of €10. Anyway, 2 have been cut down. 4 of the coins are Norman coins, which makes absolute sense. 1 fragment, the small fragment, seems to be of Emperor Frederick II. Now, Emperor Frederick II, who many of you may have heard of because he was Frederick the Great, the Crusades in the Holy Land and all that. I mean, he was one of the big warriors, kings of medieval times. Frederick the Great is mentioned as having worked on the Castrum Lecce. I showed you the document before, an excerpt from the document. So I think what we're having here is the period of Frederick the Great, first half of the 13th century, destroying what was left of the Norman castle because he wants to build bigger and better, fitting for an emperor. And so that's what happens. So now we have, well, those are the Norman contexts that I showed you before, but let's see if the next slide has them. Yes, okay. 13th century structures. These great, big, straight walls, lovely walls, you see. I know it's a hodgepodge of walls there. I can understand it. Not everybody, perhaps, can understand it without being told what's happening. Oh, I mentioned the document again, the Reparatio Castrorum, which means renewing the fortifications, which dates to 1241-6 in the reign of Emperor Frederick II, which we've identified through that coin, saying that he will build the new castle, the new fortifications, but they will be the responsibility of the town, the Universitas Lecce. And it's obviously a period of splendor. We have very, very interesting decorative vases being imported from Sicily, for example. I mean, here's an example. We have a lot more. Frederick is trying to make Lecce, I think, into an important court. At the same time, I think always Emperor Frederick decides to, I think the arrows have moved here. I don't know what's happened there, the slide. Anyway, doesn't matter. At the same time, Frederick II decides not just to work on the castle here, but work on the whole wall circuit. Now, you remember I told you that the Roman wall circuit was no good in the early Middle Ages under the Byzantine because it was too big and there weren't enough people. But when we get to the time of Frederick II, there are enough people. So he's going to restore the ancient Roman walls. He's going to better the ancient Roman walls, and that's what he does. And in the map, where it says Fortificazione di Tasfeva, you are looking at new build, which can be seen there in the wall park on close to the road to Brindisi. You can see all the remains. That grey wall there with a ditch on the outside, which you can see here in the slide, are built by Frederick II. Here we are. This is the slide I wanted to show you. This is real archaeology. This is how the archaeologists will date his layers through stratigraphic sequences and finds. You see, we have the wall of Frederick. You've got one workman in an orange, dressed in orange at the end of the wall of Frederick. Behind the workman, you have the ditch. The ditch has been backfilled, and you can see a section here in front of the cut of the backfill of the ditch. And in that, we found a coin of King Ferdinand II the Catholic. We're talking about the 15th, 16th century. Whereas where the workman's working, he found a coin of Emperor Frederick II, which is 13th century. Well, that makes a lot of sense, because the coin above, which is earlier, is dating the area of the walls built by Frederick. Whereas the coin below is dating the destruction of the fortifications built by Frederick a couple of centuries later. And that's why I've got a later coin in the fill. But I don't want to teach you too much archaeology, otherwise you'll become archaeologists and I'll lose my job. What else? Torre Mozza. So we move back to the castle now. We move back to the 14th century, and we're back in the room just behind us. And the Torre Mozza was originally built like this, with 3 floors, very nice decoration. You can still see some of the decoration if you go in to the Torre Mozza. And that's worth having a look at, because that is typical medieval 13th, 14th century decoration of very high quality, probably made by people brought in from France. This building, the Torre Mozza, it's called Mozza because it's short, because there is the other tower on the other side of the courtyard, which is taller. So it's as though this tower was never finished or was shortened at a certain stage. That's what Mozza would mean, the Italian word, Torre Mozza, short, stunted tower. But it's a very nice tower. And in the tower, there are some interesting graffiti, which I have spotted. There are probably others to be found. But in the passage between this room, which is the throne room, the Sala, and the Torre Mozza, one day, just walking along, when the sun was hitting the stone at the right angle, I saw that. I don't know if you can make out those scratches on the limestone. Now, those scratches on the limestones show 2 helmets. One helmet, the one on the left, is in very good condition. It's a very nice helmet. And on top of the helmet, there are some pottery jugs. Looks a bit stupid, actually. I mean, you imagine a soldier at a knight going around with his helmet on his horse and having 2 pots on top of his helmet. But that sort of thing happened because families would find symbols that would signify their family. There's a famous Italian family called the Pignatelli. Pignata means little jug. And so the Pignatelli knights have shields and symbols with 3 little jugs on them. You see other with rampant lions or griffins or swords and axes. He said 3 little jugs. This guy had 2 pots on his head. But the interesting thing is that these 2 pots are German pots. These 2 pots are what we call Ratskanner. A German will tell me how to pronounce them, that come from Siegburg. So what we're probably having is a German knight who's come all the way to Lecce, clippity-clop with his horse, because no trains and planes then, to visit somebody here in the castle. So we're in an international milieu. I mean, this castle was important on a European scale. What else do we have? Well, then the same Torre Mozza, but right down below ground level. You have the first level, it's halfway cut into the rock, and there are hundreds of graffiti. Nothing as exciting as the guy with the pots on his helmet, the potty guy. But these graffiti are fun because they represent various families, they represent Hebrew community, some of them are pornographic, some of them are just counts, some of them are pictures of boats and ships. But what we have are prisoners, because the lower part of the Torre Mozza was used for prisoners. Probably 15th, certainly 16th, 17th century, to stick them in there. And there were some very important prisoners in there, including the architect of the castle under Charles V. He got into bad waters at a certain stage, and so they just stuck him in the Torre Mozza, and that was that. So there are lots of things to see. And lots and lots and lots and lots of finds. Lamps galore, precious Maiolica from Tuscany, lusterware with gold lusterware plates from Derut in Umbria. We're talking now about 16th century, 15th, 16th century more or less. A Nuremberg trade token, also from Germany, the only one found in southern Italy, got all the way down here from Nuremberg. But getting back to the excavations, because I haven't quite finished, but don't worry, I'll let you off very, very quickly. In the center of the excavations in the courtyard, I found next to one of the walls of King Frederick, of Emperor Frederick, I found a drainage ditch. Here, which stops with a well, and the well takes you down to the natural water level. And at the other end, here, there's a big cistern and this semicircular stone. The semicircular stone, which you can see there, is part of a millstone for grain, I think, to crush the grain and make the flour. What we have is a water mill, which is interesting because we know from a document that the castle had a medieval water mill, and we have found the medieval water mill. I still have to reconstruct it, but it looked roughly like this. This is an Norman undershot water mill, which is attested in documents in the UK, and we have the same sort of thing. And in the end, you have this great big vat where the water would come out after the paddles of the mill would convey the water, and somebody in there has gone and scratched things all over the place, which we have to still try and decipher. This is just the part of the walls of the castle which are still medieval and well preserved, but you can't see them. We can move ahead. And then we have the underparts of the castle, or the exterior, the galleries and roads around the castle. Now this is the South Gallery. The South Gallery is the gallery just past that wall. If you go past the rooms are the scissor rooms, and then the wall, and then you'll see the outer fortification. Between the outer fortification and this building, there's a road. Beneath that road, there's an underground gallery. The gallery runs around 3 parts of the castle, and the gallery served to keep horses, equipment, food, arms, whatever was needed. So we had to dig all of that as well. And in this part of the gallery, we were able to see the remains of the town ditch, which was cut when the castle gallery was built. I don't know if you can make it out, but you see we have here, this is natural stone, here's a cut, this is filled in stone, filled in, and natural stone again. So we have the ditch of the wall, which has been intersected by the cut of the castle. Then we have beneath us the main castle cistern with a lot of finds. You can see the water level where it usually stopped, halfway up the pillars. Lots and lots of finds of pottery and what have you, and these are particularly interesting because they belong to main families. People who live here know that the Del Balzo, the Orsini, the Dengen were all important noble families. I mean, they were the top of the top. Many of them of French origin, and they commanded the politics, local politics in this area. Maria Dengen, woman, she was actually, at a certain stage, she became Countess of Lecce, and then she became, with her second husband, Queen of Sicily and Naples, the 2 Sicilies, so she basically could run the whole of southern Italy. So this is our reconstruction of what the castle looked like before Emperor Charles V did his work in the 16th century. This is probably 15th, 14th century. Rather different, but parts of this building are incorporated in the actual building, including the Torre Mozza, which is the tower here to the right, which is the tower there. What else? Well, protagonists of the new post-medieval world. Things were changing. The Middle Ages start changing. This chap, Christopher Columbus, apparently goes and discovers the Americas, for better or for worse. And, well, that means, of course, a lot of money, a lot of imports. It means slavery. It means tomatoes or tomatoes, potatoes or potatoes, and lots of other things, gold, silver, wealth, which helps to fuel the Western economy. And one of the people who was able to make the most of this is Emperor Charles I, the person who rebuilt this castle, who had his own problems because in the Mediterranean we also have Suleiman the Magnificent and other Turks. This is Sultan Mehmed II, who in 1480-81 conquered Otranto, just down the road. One piece of Italy for 1 year was part of the Ottoman Empire. Then they were kicked out. And then they tried to get back into Western Europe with 2 sieges at Ravenna. But obviously the Turks were a problem. And the fact that Turks were a problem, you see, the Ottoman Empire is expanding exponentially because of the problem. So a lot of money was spent on fortification, and a lot of money was available because of the New World. And so building left, right, and centre. This is from an excellent book by a certain scholar called Ian Morris called The Measure of Civilization. published in 2013, where he tries to estimate the amount of military spending between East and West across the globe to see what were the most critical periods of money availability and investment in the army, in military spending. And you will see West up and down, up and down, up and down until we get to 1,500, and it shoots up. The amount of work, of building, of construction, labor that was accomplished under Emperor Charles V makes, I think, even the pyramids seem like a Sunday chore, because castles all over the world. Remember, he was the emperor about whom they said that the sun never sets on his realms across the globe. So he built the new walls of Lecce, and he built the triumphal arch of Porta Napoli that you may have seen, and he rebuilt the walls of the city, and here we are, some slides of the walls of the city, and I like to show people this slide because here we have an image found carved on the walls of the city that you can see if you go and see the walls, that are very, very important, because the one above, F.D. Loffredo, refers to Ferrante Loffredo, who's governor of the province of Puglia, and who was responsible for actually overseeing the building of the walls. Whereas on the side of the walls, we have this rather rough-looking scratching, which, to me, to my mind, reminds me of the famous painting by Titian in the Prado that represents Charles V. Perhaps Charles V is represented on the walls of Lecce. I think I am now close to the end. I think I want to, yes, I won't bother with these things because we have bits and pieces of things that are found, such a medieval 14th century bell casting pit, which is important for technology, the East Corridor, which is important for building, our study of building, an anti-mine gallery, which were these galleries built around the castles. If anybody tried to dig a quarry, a tunnel to get into the castle underground, they'd find themselves trapped within these galleries where they could be killed off. And it was quite a sophisticated piece of work. South Corridor, South Gallery, all the soil we had to move, and in moving all that soil, we found also a wealth of items that take us up to today, with things of the First and Second World War, when this castle, the underground rooms of this castle, became air raid shelters for the people of Lecce. So we have dog tags, bayonets, the fascist coin, medicine, bullets, and then I finish with the so-called Liberty Canopy, which was a market, an iron and bronze market canopy built against the castle, I believe in 1898. It survived for many, many decades, was then removed a few decades ago for restoration, and will be remounted again in very close by. So thank you very much for your attention, and I hope you have a good conference.
Thank you very much, Paul. I think that, we just had the poster session in the Torre Mozza Professor Arthur was talking about. And so for us, it was the poster session site. And so you remember that the first day I said that this is a very important monument with a lot of history behind it. And so now you see what I meant. And also this room is the Sala Maria d'Enghien, which is named after the Maria d'Enghien, which was the queen of the reign of Sicily. I do not know if you have some curiosity or questions. And no, Walter Kuchera.
Well, thank you very much for this beautiful historical overview of your country here. I was just wondering, how did the Normans disappear again? The Normans came to Italy all the way to the south. Also, how were they driven away, or who was the power who got rid of them?
Well, basically, it was a matter of the various power groups. I mean, they just lost the power. They didn't all disappear. In fact, well, when the Normans came here, they were probably not in large quantity, and a lot of their soldiers in this area were probably locally employed, so not even of Norman origin. The knights would have been Norman, the governors would have been Norman. They would have become the landowners. When power changed at the end of the 12th century, they lost their positions of power. Some were killed if they were particularly obstreperous, but others would just sort of fade away. Even today, we have some surnames, some South Italian surnames, that are quite clearly of Norman origin, of people who have survived as families, but are landowning families or now do other things. It's a regime change, but not usually a total destruction of the population.
Okay, thank you very much.
Thank you. Just one, Elizabeth.
Yeah, well you know, the story of the tree of the fava beans.
Yes.
The picture, the image that you show is from my paper with Valentina Caracuta. And those beans are 10,000 years old.
Yes.
I dated them, you know.
Yes.
So, and they were cultivated already in 3 sites in Israel, Achiud, Tzipori, and Iftachel. So I wonder, they were continuously cultivated there in the Near East. What is the base that we need the Normans to bring the fava beans back to the Mediterranean area?
Well, the thing is that this work is the archaeobotanical work is being done by Girolamo Fiorentino, who you know, and Valentina Caracut, of course, was one of his students and then left. And Girolamo says that the closest parallels he has, I mean, that those are the small fava beans, but they are the largest of the small variety, if you know what I mean. And the examples of the largest of the smaller variety he knows from the castle here in Lecce, from a site in Sicily, which was discovered not very long ago in a big sick transit project, and from Normandy. And the annoying thing is that, of course, what we've got is an amelioration of the fava bean, but it's hard at the moment to understand where the amelioration comes from, if it's purposeful breeding to prepare better crops. But of course, I said it's not just a matter of having bigger beans, but it's a matter of having something that can help fix the azote, or the nitrogen, to the soil to what's the word now? Improve what is not a particularly fertile soil, such as that of the southern Mediterranean. So it may have been a specific, rather than being coincidental or it may have been a specific ploy to try and ameliorate agriculture, because the Normans did bring in other things like crop rotation, 3-year crop rotation, and various ameliorative actions. But I'm glad that
Thank you very much. Let's thank Professor Art. Okay, now for just two announcements for those of you who booked the walk-in tour. The meeting point is just at the entrance gate of the castle in about 10 minutes. And tomorrow morning, if you can be here a little bit earlier, let's say 7:45, we will leave not before 8:30. But if you can be a little bit earlier, because we have to somehow arrange the bus and so on. Okay? Thank you very much. Grazie.